Alright, hell yeah. So we have a physics question that I propose, you know what I mean? Why don't we crash into the sun? And if we answer this question, I think it'll kind of open up a few doors for us of understanding, you know what I mean? Before we get that in. This is going to be a video about F equals ma. You know what I mean? This is the gold standard. And unless your masses that we're analyzing are tiny enough where they fit into like a quantum physics model, every particle in the universe that has mass obeys F equals ma. And over here we have acceleration. Most important thing, you need to write what acceleration is. I do this: change in velocity, change in time. What this equation says is if we you know what I mean, from our textbooks, if we can identify things that cause force, and you know what I mean, we have like a net force, and examples of that would be, hey, you jump off a cliff. Well, holy Toledo, there's no other forces around. Even air is just air drag. Force of drag is zero when you jump off a cliff. I mean, for the most part, jumping into a water. So the only force on you is gravity. And in a lot of the textbooks, I don't think this does it a good service when they just say it's mg. Because it kind of looks like that side of the equation. You're just like, what the hell? But this one just happens to be mg, and it doesn't need to be. You know what I mean? You have other forces. You have like the force of a spring is some spring constant times its position. You know what I mean? That doesn't look like mass times acceleration. But this force of a spring would go into this side of the equation. This mg actually goes into that side of the equation. And you're just like, what? So that's probably the most confusing thing. And so we're doing this video because there's no reason to make 4-hour videos. People just watch a couple minutes. Because I'm going to use this in the other video that I want to do, like impact loading. And you know what I mean? Like here would be the question for that. We drop something, gravity is going to, you know what I mean? Hey, you have a force of gravity on this. F is equal, I mean the force of gravity is mg. Cool. And then you have F equals ma. So with this, we have a force of gravity over here. There's no other forces that are, you know, holding it up. I mean, you could hold it up with your hand, and that could equal the force of gravity. You could do that, but then you could let your hand go. That weight is going to fall because F equals ma. Because you have and that's where you get into, like, it's probably better to write this as net force, especially if you're not going to put any, like, vector signs on it, or you know what I mean. So we just have net force is, hey, we've identified that mass. This is the mass that we've identified, and we are going to have an acceleration. We're going to have a change in velocity, change in time. So so give it a second, this thing is going to change its velocity. It's going to go from velocity of 0 to some velocity. You know what I mean? And we know that gravity is 10 meters per second. Per second, you know what I mean? Okay, so back to our question. Why don't we crash into the sun? Okay, and so this question comes from, you know what I mean, it's like, well, we know from that the force, so I'm going to say this force of gravity is mg. Now, where does that come from? It comes from Kepler's equation that the force of gravity is the gravitational constant. The mass that you're kind of like, hey, that's me, that's my mass, you know what I mean? And then the mass of the Earth. And the only reason we have gravity is we have a huge, you know what I mean, huge Earth underneath us. And so, and then there's a distance from the center of this mass to the center of that mass. And for all purposes, if we're on the surface of the Earth, that is just the radius of the Earth. It doesn't matter that we're standing on top of a cliff and, like, hey, like we're jumping into the sea and we're considering sea level, you know what I mean, where the radius of the Earth stops. This thing is really big. It's 6 million meters. It should be a good number to memorize, but 6.37 times 10 to the 6 is 6,370,000 meters. Cool. And it doesn't matter that you just decided to jump off a 40-foot cliff. You know what I mean? Another 10 meters to 20 meters. No one cares. Well, and then that radius is just what? What are you going to add 20 meters over here? You know what I mean? Who cares? That's not going to influence the problem. And I'm sorry, right here, I didn't even finish my equation. This is the radius of the Earth squared. Cool. And I think we get this. Hey, any two masses in the known universe are going to have a gravitational attraction between them. And if you just pin the Earth into outer space, like, hey, it just looks like there's going to be a force on us. You know what I mean? Well, there's also a tiny, tiny force, like, you know what I mean, kind of nudging the Earth your direction. But that's probably the first one to analyze. Mass times acceleration. So, well, isn't the Earth getting nudged? Sure, but the Earth has hella mass, and we can use this equation. Once we solve this equation, we're going to find the force in newtons of this. So well, let's do that. You know what I mean? Because now I probably have you like, you're like, whoa, well, isn't like you know what I mean? Yeah, I think you see where we're going with this. Maybe. All right. So the force of gravity is gravitational constant. Now, how do you remember these? I don't even think I wrote it right. No, yeah, 6.67. Just think of the devil. You could write it 6.666 times 10 to the negative 11. My mass, 70 kilograms. I'm not putting units on that, but everything's in meters, kilograms, and seconds. You know what I mean? Okay, and then the mass of the Earth, good one to memorize. It's just 6 times 10 to the 24. More sixes. You know, we get it. But it's also 5.94 times 10 to the 24, if you kind of want to memorize. That's in kilograms, who cares? You know what I mean? I think it's better, like, I'm going to teach you to not use, I mean, always do a double check on your reality of your units, but the more things you write, actually, probably the more mistakes you're going to make. All right. So 6.37 is the radius of the Earth squared. So this is where I make the mistake all the time. I just get tired of writing, and then I forget this squared, and that'll mess me up. So yeah, a lot of sixes, 666, 6, 6, you know what I mean? And this is 6 squared. Yeah, we get it. So it's a pretty good way to remember that, you know, science is of the devil or something like that. I don't know. That is just kind of interesting. But didn't we say force of gravity is just mg? And isn't our mass 70 kilograms times g? Well, yeah, okay, so that's where all these three terms don't change. This is the gravitational constant, you know what I mean? It's got don't change in its name. And then the mass of the Earth ain't changing. It's cooling down and stuff. I think it's going to get a little bit less mass. But anyway, and then the radius of the Earth doesn't change. You know what I mean? So those three things are g, and it's just fascinating that they end up to be 10. And, all right, well, let's do it, because it's just kind of fun, you know what I mean? Because we have 6 times 10 to the negative 11. Now we're just trying to prove that that's just 10 to the 1, you know what I mean? And then this is 6 times 10 to the 24. And then this is 6 times 10 to the 6 squared. So that's you could just write it 6 times 10 to the 6 again. But yeah, any way to just see that those 6's cancel those 6's. Cool, so now we're just left with 10 to the negative 11. And then we have 10 to the 24. And then we got 10 to the 12. You're just like, well, are we getting closer to 10? Doesn't look like it. But hey, this 10 to the negative 11 is also just 10 to the 11 downstairs. Cool. And now we these add up. So that's going to be 10 to the 23, 10 to the 24. Oh, booyah. That's just going to be 10 to the 1 up top. And we get gravitational constant is 10. Now, that's important because, you know, even as a student, you just won't pull out this equation because no one wants to memorize the gravitational constant or the mass of the Earth or the radius of the Earth. But those three numbers are worth memorizing, and I came up with a pretty good axiom. Just think 6, 6, 6, and, you know, if you call this 6 and you call that 6, you're good to go. And then gravitational constant, hell yeah, that's where it comes from. Just 6, 6, 6 will get you real accurate. And if you don't know this is negative 11, well, how the hell is it all just going to balance? You know what I mean? This is going to be 6 times 10 to the 12 after, or I mean 36 times 10 to the 12 after you square it. And then this is 10. You know, you could get that relationship that this is negative 11 if you forgot. So that's the cool thing about my method on that. Alright, so yeah, let's complete this equation, because all this equation is going to say is that we have 70 kilograms times 10 meters per second squared, you know what I mean? And so now what? Well, we need to figure out the units of F equals ma, because we just set these units based on, you know what I mean? F equals ma isn't F equals a constant times ma. Now, because this comes up a lot, because, hey, the force of a spring isn't just force times distance, because you can make a spring out of a lot of different things. And one of the viewers is just like, yeah, I don't have a set basis of what this is for, you know, the spring constant or elasticity of materials. But yeah, in material mechanics world, this is EA divided by L. You know what I mean? Those three things, the area, length, and modulus of elasticity. We're not going to get into that. That's for a separate video. But hell yeah, F equals ma doesn't have any sort of constants out front, just because we set it to be so. We set that the units on this is 1 Newton, is 1 kilogram, is times 1 meter per second squared. So if I find a height above the Earth where I can drop a 1 kilogram mass, and I know that my acceleration due to gravity, g, is going to be 1 meter per second, you know what I mean? That would be another math problem that we could do. And so let's do that one right now. You know what I mean? But the other way to do that is just, hey, we have 1 kilogram on an icy surface, and I want, in 1 second, I want it to be going 1 meter per second, and that's about 2 miles per hour. 2.5 miles per hour, you know what I mean? And then, so how about 2 seconds? So I want it to go 4.5 miles per hour. So I want that thing to go 4.5 miles per hour in 2 seconds. Well, I would have to put a force of 1 Newton, which is about a quarter pound, on 1 kilogram, which is about 2.2 pounds for the Americans, you know what I mean? And I'm an American, you know what I mean? Engineering sucks because we don't know anything about meters per second. But even in Europe or Canada, you don't drive in meters per second, you drive in kilometers per hour. So still there's a funky conversion there that you have to get used to. All right, cool. And yeah, we're not going to solve that one, you know what I mean? Well, let's take a pause. Yeah, that's crazy. Anytime I'm just like, well, I'm not going to solve that one because it just seems like a little bit of work, or like I might, it's either a little bit of work, I might make mistakes, and then it's just going to get into like finding mistakes. But no. We're good because we're trying to figure out why the force of gravity is what it is. You have the Earth, and we're always near the surface of the Earth. Now, this is going to make a lot of people feel claustrophobic, but yeah, you live in a zone. You can get to the top of Everest if you pay a lot of money and you're in decent shape. Or, I don't know, you could go into a deep cave somewhere. I don't know. You know what I mean? You go, I don't know. But basically, your whole life is just lived in that little layer. You know what I mean? That'll make you claustrophobic as hell. You're just like, oh, I feel trapped. You know what I mean? Life is just in that zone, and it's literally just, you're always going to be that far away from the radius of the Earth. You know what I mean? Unless you got big bucks to, you know what I mean, trap yourself up into the space station. You know what I mean? Those people are still up there while I'm making this video. No, I just think that's funny. You know what I mean? Well, you know what I mean? It is what it is. People are adventurous, and that's cool. You know, we'll find ways to, we value human life, you know what I mean, at the utmost. So if you're still alive, we'll try everything we can to keep you alive. That's pretty cool. But yeah, for the rest of us, no. You know, you can go 7 miles up, 7 miles, because everyone travels in planes. I think we've all gotten to do that at least once, hopefully, because that's a pretty cool experience, you know what I mean, flying a plane. But yeah, that's the zone that we live in, and so I've always wanted to take a scale up to a plane, you know what I mean, weigh myself at the tarmac, and then, or just even on the plane before it takes off, and then pop out my bathroom scale at 7 miles up, and then see how much I weigh, because my radius away from the Earth is going to be less. Cool, you increase that radius where the force of gravity is 1 Newton, you know what I mean? So, so let's see, because there's a couple things going on here, because I just said this is in this side of the equation. So, because I'm trying to like even answer my own question. So we're going to put this force of gravity into that side. So we have gravitational constant the mass that we're analyzing, mass of the Earth, radius of the Earth squared. And that's going to equal the mass that we're analyzing times the acceleration. So usually when you get F equals ma, for your books, especially if you have some sort of mass, you have identified some sort of forces, especially if it's like a ramp problem, you know what I mean, like this or like this, you know what I mean. Hey, we've identified masses, we've identified forces. But you know, like the component in this direction ain't doing crap. It's just going to compress the molecules of that block. But hey, there is a component. So of this, you have two components. You kind of do dashed lines for the components. But there is a component that way. And if this is an icy slope, hell yeah, we have a smaller component. And what was this? This is the force of gravity. So we had mg, which by definition is the most force. If you jump off a cliff, that's the most force you can be experiencing in the direction that you're moving. But if you're on a ramp, no, you're just going to experience some sort of component of that force. So if you're sliding down an icy slope, you black diamond, and you're just like tucking it, that's going to limit your change in velocity. You know what I mean? So even on your black diamond, you're not going to be in free fall. So that's kind of, that answers that question, because that was kind of like people wanted to know about the kinematics, you know what I mean? And that's the first one. Everyone's jumped off a cliff, and that, or hopefully you have, because that's wild. And it's just like, whoo, you know what I mean? You kind of start out slow, and then you go hella fast, and the air time is crazy. But then when you get to a bunny hill skiing, you're just like, oh, I'm not moving or something. But then you get to a steep slope, you know, maybe a blue where you can just tuck it. It's amazing. You can just go down the hill. But your speed is limited by the component of gravity in that direction. You know what I mean? So if you have, and we can probably do this pretty simply, because yeah, this will be a good tangent to go on. So we have a 30-degree slope. That's steep as, even for skiing. But you might be able to tuck it just for a little bit, right? And then so you have and hopefully this comes out fairly decent. So gravity is going to be straight down. You know what I mean? If we put these coordinates on, like this 30, you'll just have to trust me. Well, then that's why we try to make this angle a little bit smaller, because then we can be like, okay, that looks like the 30-degree angle, theta, and then I'm going to say the other angle's phi. So there's a 90, phi plus theta equals 90. All right, hell yeah. So, I mean, but here's your force of gravity. That's going to be your mg down, and then we only have a component. We have a component that way, and then a component this way. So if here's my angle, the sun is shining on the component that way, cool, it is working out to my benefit. So if this is 30 degrees, sun is shining on the sine, so we have sine 30. What do sines and cosines mean? They're percentages, you know what I mean? They're fractions between 0 and 1 of the whole vector. So I know mg is the most force of gravity that I can put on my body to change my motion. Back to F equals ma. Force of gravity, hell yeah, I'm a mass and I want to change my velocity. We'll jump off a cliff and your change in velocity, change in time, is going to be 10 meters per second per every second that you're in free fall. You know what I mean? Hell yeah. But if you're just on skiing and you're on this slope, only the component in the direction that you're actually traveling is going to be worth a damn. And it's just cool. I love the relationship with sine 30 because it's the only angle that comes out nice. But it's half. It's 50%. Sine 30 is 0.5. So only 0.5 or half of your mg is taking you down the hill. So now what happens? Well, if I said falling off a cliff, mg is 10 meters per second, and no one lives, I don't know, maybe, well, I live in America, and sometimes I just assume, oh, everyone lives in America. No one lives in America. Okay, so but 10 meters per second, what's that to miles per hour? It's a good one. 22 miles per hour. I have a video on factor label method. That would be a good one to do. You know what I mean? Go do that yourself, just so you can see that 10 meters per second. Hey, pretty close. I think it's like hella close to 22 miles per hour. Said it wrong. So cool. You jump off a cliff. A second later, you're going to be going 22 miles per hour. 2 seconds later, you're going to be going 44 miles per hour. And that's going to be a check on reality, because that's basically the speed that you'll impact the water for most cliffs. And for most jumping off problems, you can't sustain 120 miles per hour. Because if you could sustain 120 miles per hour, you could skydive and just land into the water and just be scot-free. But no one can. You know, I mean, very few people live from falling into water from skydiving. You know, there's just fluke cases of survival. And so, how big of a cliff? You know, neglecting air resistance, because really air resistance, well, no, that's the definition of air resistance. You will have air resistance. Your acceleration will be 0 once you hit 120. But let's say that's not the case, and you're going to increase 22 miles per hour every second. Well, 120 divided by 22. Hell yeah, it's going to take 5 seconds, 6 seconds to get to terminal velocity. So what height of cliff would that be? Because this is the other thing, just to like rattle off the basics, is if at one point, let's say it takes 6 seconds, you know what I mean, and then we go back to meters per second. I think that's a good thing to do. Because we have, if you jump off a cliff, that you know your air time is going to be 6 seconds, which is kind of in that fatal zone. And we'll see how high this is. It's just fascinating. Where it wouldn't matter if you jumped off a cliff that took 6 seconds or 8 seconds. Because of terminal velocity, you know, I mean, you could kind of do that. You're going the same speed upon hitting, you know, the water, let's say. Let's say you got a special egg suit where this is humanly possible, and so the problem doesn't breach insanity. Okay, so we have 6 seconds. And go back to gravity 10 meters per second. So just mentally, you can be like, well, every second, I'm going to increase my velocity by 10 meters per second. So I'm going 10 meters per second, 20, 40. I mean, I can't do math. But anyway, you do that, you're going to be going 60 meters per second. And 60 times 2.25, that's like times 2 times 25% tip, that gets you pretty close. You're going to go 135 miles per hour. But yeah, our goal is just to go 120. That's terminal velocity for most skydivers in kind of normal skydiving positions. All right, so that's going to be my speed, 60 meters per second upon hitting. And look at this. My initial velocity is 0. So this is where I draw this chart, and I think you should too. It's just really good and intuitive. I'm in a car going 0 miles per hour, and then I'm going to slowly increase my speed to 60 miles per hour. And it's kind of a bizarre one because no one would drive that way. But the question is, like, how far are you going and what's your average speed? So my average speed, it should be pretty easy to see, is going to be 30 miles per hour. And then how far do I go? Well, it's like I'm going 30 miles per hour for a half hour. So I'm going to be going 30 miles. So we do that same thing to figure out distance. Now that's the intuitive approach to figure out the kinematic equations. You know what I mean? So let's because the viewer is just like, yeah, can you share kinematics? So, like, you can do that in your head, well, I'm going to do this, but yeah, we can say that our acceleration is 10 meters per second. That's acceleration of 10, and then we say acceleration definitionally is dv dt is equal to 10. We separate variables, so we get the dt over here and integrate. We get velocity equation is equal to 10t plus our initial velocity at 0. Okay, sweet. So then we integrate again because we know that velocity is change in position, change in time. Now I'm just doing this fast because this would be a whole separate video, but it's good to, once you do this approach, be able to get there quickly, because now we're going to separate variables again and then integrate, and we're going to get an equation for position, which is what we want, is equal to 5. It's 10 divided by 2 because our t integration goes t squared divided by 2, and so we got the acceleration of 10 divided by 2, so we got 5t squared plus our initial position. We're just going to say we're 0 up here, and we're going to say this is the positive, positive number is going to give us our height of that cliff. Cool. And then so, because that would be the constant portion, when time is equal to 0, our position is 0. And sorry I didn't spell that out. When you integrate, you do have a constant, but then you throw in time is equal to 0, and our velocity is 0. We just jumped off the cliff. Okay, so right here is our position equation. So we can just easily do this. We can be 6 seconds squared. So we have 36. 36 times 5. That's the same as 18 times 10. And we are 180 meters off the ground, which is pretty wild. 180 times, what is it, 3.3 is 600 feet. You know what I mean? So that's Yeah, it takes a huge thing to get up to terminal velocity. And again, as you reach terminal velocity, you won't be accelerating no more by 10 meters per second. All right, so let's solve that one by using this approach of like, well, didn't we say we were going 0? And then at hitting, we're going to go 60 meters per second. So we're going to have an average speed of 30 meters per second. And we're going to be traveling for 6 seconds. So hell yeah. So if we have an average speed of 30 meters per second and travel by 6 seconds, seconds cancel, and you get 180 meters. Cool. So that's what we get from the... kind of I call this the who cares approach. We just guess. We know there's some integration, but it's a linear relationship. So all you got to do is divide by 2, which I'm doing this video because the work energy comes up a lot. And like if you have a spring and then you put some force into it and it changes a distance. Well, a spring, when you put like 0 or just like a very fractional amount of force, hey, it changes distance. And energy says like energy is force times distance. Well, right off the bat, you're just putting just a tiny, tiny amount of force. But then let's say this is going to be like 1/10 the distance. Cool. And then what happens at the end? Well, as you push into this, the force needed, now you have like force max, like right at the very end. So at the very end, now you have force max, like that max force still times 1/10 of a distance. Well, look at this, this is almost 0, and this is something, this is a big number times 1/10. And then, it's just like, hey, I'm going 0 miles per hour. How far did you go? Well, hey, I just got out of the driveway. I'm going 0, don't ask me that question. That's a dumb question. But hell yeah, over here, for the last, like, minute, going 60 miles per hour, we know that 60 miles per hour for a minute, hell yeah, I'm going 1 mile. Which is a substantial amount of that trip. Getting out of the driveway is nothing, Like, no one's even going to quantify that as a distance. But then, hell yeah, the last mile, when you're just like, let's get there, and we're going top speed, hell yeah, you just went 1 mile, 1 full mile. And this is a bizarre one. No one's going to travel, like, no one's going to go from 0 to 60 over the course of a half hour. That would be a bizarre one. All right, hell yeah. Take a little break, but we're back. And so the direction we're going to go is we're going to go back to this one. We wanted to know the units on F equals ma. And so we're going to make, this is the Earth, we're going to make a huge tower where gravity is just 1 meter per second squared. And how do we relate that? Like gravity is 10, and or 9.8 if you're just like, hey, But 10, and then isn't the gravity on the moon 1/6? So what's 10 times 1 divided by 6? Well, that's a gravity of 1.6 meters per second squared. All right, so this gets us pretty close. So if we make a huge tower that we don't know what the radius is going to be, and we got 2 things here. Just we have the height of the tower. Maybe we say that's h. But that doesn't go into this equation because the mass of the Earth is down there, and we have the radius of the Earth plus this height. That's going to be the total height right there. Okay, and if we do make this tower that makes our gravity, this component, 1, which is pretty close to the moon, we'd be standing up there, and then if we jumped, it'd feel like you were just jumping on the moon, but even less. Like obviously it's less. It's 1 divided by that, or just inverted that. This would be 60% of the gravity on the moon. So all right. So but if you're up there, yeah, you would jump, and then you would you'd jump pretty high, and then you'd fall back pretty slow. Your velocities would be pretty slow. Okay, and so let's solve for that. So again, we have Kepler's equation, force of gravity, gravitational constant. I gotta get a new pen. Alright, hell yeah. So I do like these pens, Pilot G2, the number 10. But yeah, the ink just goes all the way to the bottom. But that means you get to use all the ink in the pen. But they definitely run out. Okay, so we have force of gravity, gravitational constant. Mass of us, mass of the Earth, And then I'm just going to say radius. In my last video, it worked pretty good. I just called this radius big. You know what I mean? Put an acronym on it. So that's kind of like your asterisk. That is a huge place that you can make mistakes. But this is no longer the radius of the Earth. This is just the distance between me and the center of the Earth. So that's going to be the radius of the Earth plus the height of the tower. You know what I mean? So those two things are going to be that distance. All right, and let's write our F equals ma equation. And the reason, like this is going to be the force on us, and we want that force to be equal to 1. So, this is fascinating. Holy Toledo, because it goes back to the units, and I think it can get kind of confusing. We have a force of 1 Newton is equal to a mass of 1 kilogram times an acceleration of 1 meter per second squared. So yeah, I knew something was up, so my bad. If this is the Earth, and then this is our huge tower, we are just dropping a 1 kilogram mass, you know what I mean, maybe a small little block of steel, or a brick or something, off, and then it's going to fall at 1 meter per second. It's going to have a change in velocity of 1 meter per second every second. So, which is interesting because, like, this is visually fascinating. Because if we do the problem where we jump off a cliff in 2 seconds, we're already going 44 miles an hour. We're already going 20 meters per second because acceleration of gravity is 10 meters per second squared. And, well, let's do that one real fast. We had in our equation of x, it said that was half of gravity, so that's going to be 5 times time squared. And we're going to cliff jump for 2 seconds. So we're going to have 2 squared, that's going to be 4. So 4 times 5 is 20 meters. Cool. So yeah, remember that? This is a 20 meter cliff. But now here, at 1 meter per second, well, let's do our car analogy. So 0 to 60 in a half hour. So for this, our velocity is 0, and yeah, let's change by 2 seconds. I'm fascinated. So in 2 seconds, our velocity is going to change by 1 meter per second every second. And so another way to write acceleration, instead of just 1 meter per second squared, I really like this. It's 1 meter per second. Sorry. Let's write it again. 1 meter per second, put parentheses around that, and then divide by seconds. This is going to be your change in velocity of 1 meter per second every 1 second. So it just really spells it out. So after 2 seconds, we're going to be going 2 meters per second. And just multiply by 2.25, you know what I mean, times 2 at least. That's 4 miles per hour. You know, if you want to get techie, kind of like that 25% tip, that's how I kind of remember it. If I had a bill of $2, what would be 10% like the old days? It would be 20 cents. So 20% of that's going to be 40 cents. And then, so yeah, it looks like 50 cents. So we'd be going, times 2 is 4 plus, 0.5. So yeah, we'd be going 4.5 miles per hour. Okay, but let's get a check on reality. So at some time, change in time is equal to 2 seconds, we're going to have a velocity of 2 meters per second. And that means that our average velocity for that time, if this was 2 meters per second and this was 0, you can see that our average velocity for this problem is going to be halfway, 1 meters per second. So we have an average velocity of 1 meters per second for that 2 seconds. And yeah, you will kind of slow this down because, hey, we have speed in meters per second. We know that we go for 2 seconds. We have two things in that we want to either multiply them or divide them to get something useful. And so if we multiply them together, seconds will cancel and we'll get meters. So we got 1 meter per second times 2 seconds, and we went 2 meters. But I bring this up because with this is very fascinating. After 2 seconds, you're only 2 meters, which is about 6 feet. You know what I mean? A 4x8 sheet of plywood. You know what I mean? You drop something, and in 2 seconds later, it's there. That would be the cool thing, like at a high tower, that you could take a, you know what I mean? an elevator to the top of on Earth or something. It'd just be fascinating to experience that, especially if it was something close to Earth, because you're like, hey, we're still close to Earth, but we're experiencing that. And I guess all it would require is you know, something more powerful than a plane. You know what I mean? Something to get you higher, and that's what we're going to solve. We're going to solve what's that height. And yeah, like maybe I don't care about going into outer space. I just want to go to this height. Like that's my goal, because I want to be on board of something that at least has a height of 8 feet ceilings, and then drop something from there, and then see that it takes 2 seconds. Like drop it, 0. I mean drop it, 1, 2. It lands. I mean that's just very fascinating to me. Like you drop it, 0. 1, and it'll take 1 second to maybe get to there, because it's a non-linear thing. So because you can even do the equation. The equation for this is x is equal to acceleration of gravity divided by 2. So it's 1/2 t squared. So our distance after 1 second is 0.5 meters. Oh, I had that totally backwards. So yeah, our distance. If this is whoa. Yeah. How far are we going? Yeah, we're going 2 meters. Yeah, so we're going to say this is 2 meters. Yeah, so in the first second, we're just going to go 1/2 meter, 0.5. And then in the second second, so that is fascinating. You drop something, it takes a whole second for it to just go 0.5 meters, which is, you know, 1.5 feet. I find that very fascinating. The other thing on units, like, I don't know, yeah, because 1/2 meter isn't quite 1.5 feet, but it is 0.5 meters. I do know what 0.1 meters is, because that's 100 millimeters, and that's pretty synonymous with 4 inches, you know what I mean? I think mountain bike suspension, kind of in the old days, hey, I got 100 millimeters of travel. It's pretty damn close to 4 inches. So if I had 0.5, that would just be 5 times 4. We could do that. That'd be 20 inches. So there you go. So that's fascinating. So in 1 second, it's only going to travel 20 inches. I think it would be weird, you know, to be at that height where gravity is just like kind of slow. You have a mass, and its change in velocity is just a little bit slower. So now that brings up this next point, is just like, well, isn't the change in velocity going to be the same for any mass? Yes. But the reason we chose a 1 kilogram mass is because the force of gravity is 1 Newton. It's a 1/4 pound. So we're saying, hey, we have a 2-pound mass on a hockey rink. This would be a fascinating one to do. I would like to get a device where it would be like the opposite of a fish scale, you know what I mean, with a spring, where you could push into something and then push it along an icy like lake or something, and then see the force required to do that, because this would be equivalent to the force of gravity. That if you wanted to, well, and then you would have to have distance. You know what I mean? If you wanted to mimic gravity in 1 second, you know, the equation for gravity, now that we have that kinematics down, is 10 divided by 2. The acceleration of gravity divided by 2 times t squared, you know what I mean, plus a constant. Now these over here is if you have initial velocity, but we're saying our velocity initial is 0, so you know, so that component goes away. And our position, we're saying our position is 0, so that's going to be x naught. So that's where this part of the kinematic equation can just go to 0. And at a certain point, it's good to memorize that, but not off the bat. It's way better to do the integration approach to get this equation than just to spout it out. But hell yeah, so we have 5t squared for us on Earth, and after 1 second, we're going to be going 5 meters, which is pretty substantial. So yeah, you would have to push it real fast. So that's where this analogy, if you're trying to mimic Earth, would be very difficult. But if you're trying to mimic our scenario where you just have 1 kilogram, and I want to put 1 Newton of force, which is a 1/4 pound of force, Well, now I'm going to experience this. So I could do this same experiment by building a huge tower, which would be physically impossible, or just go to an icy lake and then push with a 1/4 pound something that weighs 1 kilogram, and hopefully the ice is pretty frictionless. And what we would want to do in 1 second is we'd want to go about 20 inches. So I would just do that. So you'd go 0, 1. And by the time the time said 1 second, someone's got that clock on a stopwatch, you're going to go 20 inches, and you're going to mimic what force is equal to mass times acceleration, the units on it. You're going to mimic 1 Newton on 1 kilogram, and you have accelerated it. You have changed its velocity in 1 second by 1 meter per second. So there you go. And again, if you're changing something's velocity from 0 meters per second to 1 meters per second over a time of 1 second, your average velocity is 0.5 meters, which is going to get you 0.5 meters. And 20 inches is 0.5 meters, because I said 0.1 meters is 100 millimeters, which is 4 inches times 5, and that's going to be 20 inches. So I definitely like... I definitely like to bring the America up to speed on the conversions, because else you're just not, and problems just aren't going to have that kind of intuitive sense. All right, hell yeah. So without further ado, I think we've fully explained that. Now let's just use... oh yeah, but I think we have to break out F equals ma again, because we have this Kepler side. So we have G, mass that we're trying to find the force on, and then the radius of the Earth squared. Sorry, I'm not squaring these. And that's equal to the mass times acceleration. So in most problems, you just want to know the change in velocity. You're identifying a mass, and this is dynamics. I want to know its change in velocity. I want to know its acceleration. But you'll see A, and I swear, just even that letter won't register to people. This is where, like if I say it right, Vertasium, I don't know, just hits the streets and be like, hey, do you know what acceleration is? No one does. But hell, if you're driving in a car, do you know what change in velocity is? Everyone knows that. And so at the end of the day, in all equations, that's what you're trying to find. And so what you do is just like, from the F equals ma perspective, is like, cool, F equals ma, I can remember that, but I want to know acceleration. So then I just take the mass downstairs. So I take the force divided by messed it up. So acceleration, if I just isolate that, is force, divided by mass. Acceleration is force, the net force, divided by the mass. The acceleration is the forces in the known universe. It could be gravity plus drag. Usually it's gravity minus drag. Plus the force of a spring. So just all these things. Force of gravity minus the force of a spring. So there you go. And then all divided by mass. But now you have an equation that if these are functions of time, then you can find the acceleration at any given moment. Yeah. So I mean, that's where the free body diagram comes in. So if I jump off a cliff, okay, let's analyze where my location is, and we set this 0, 0, but that's kind of not true. Wouldn't the center of the Earth be 0, 0, and the radius of the Earth is our actual position? Like, that seems normal compared to just saying, oh, no, I'm just going to say, like, where my position is 0, and then I'm just going to make up an axis, and I'm going to say this is the positive axis. Well, sure, you can definitely do that, but there's other problems where you're not going to use the top of that cliff as your datum. You'll have to use something, more substantial. You'll have to use the center of the Earth. And so, yeah, that's cool. That's cool. And so this acceleration, after you do your equation, might just be the acceleration at that location. And that's where if you do this, mg, you're just missing out on a ton. because this is force of gravity due to Kepler. It's g(m)(me), radius of the Earth squared. You know what I mean? So if you're higher, this mg is going to change. And I just think, I can't stress that enough, even just like graduating college and being like, oh, I didn't have that in my head. You know what I mean? Just, hey, this is mg, and let's just get on with life. Alright, hell yeah. And I'm glad I took a little break there, because this really does explain, like when we do this setup, when we have a 1 kilogram at some height where our acceleration is 1, we can solve for two things. We can just solve for the force of gravity to be 1 Newton, and that's kind of what we want. That goes into this side of the equation. We want to solve for this to be 1 Newton. We're analyzing a 1 kilogram mass, and so we also want to know when the acceleration is 1 meter per second squared. So you can see that we can solve this equation equal to 1 Newton, and then we're going to find our radius. We're going to call it radius big from the center of the Earth. Or we can rearrange this equation like we do. F equals ma becomes acceleration divided by force mass. You see this a lot in textbooks, and I just think doing that is just, sometimes it kind of like blows your mind or something. You're like, whoa. And if we do that with this equation, the m comes downstairs and cancels with the mass. That's why this problem, then I want to throw the 1 kilogram block off just to see it do that thing, and then I want to jump off and see myself do that thing. You know what I mean? Kind of go real slow right at the beginning. And so, yeah. And this is fascinating. Like this from the physics perspective, this is what I would ask the guy who jumped, the Red Bull dude who like jumped out at like super high height. You know what I mean? Be like, and we should do that. We should figure out what height he jumped from, and then what his acceleration of gravity. That would be a nice little short. But then the question would be, like, because there's nothing around besides the shuttle that you jumped out of, and you ain't looking back. Like, he had to concentrate so hard, but it was just like for those first few seconds, like, did it feel like you just weren't moving? Like, that is bizarre, where you jump out and you're like, whoa. I'm not moving, but I know in a little bit I'm going to be going hella fast. I think that realization, so that's what you can take from physics. You know what I mean? Physics, you can be like, whoa, that person was in that scenario. Like, hey, now I have an understanding of what that person might have felt. And I think that's exciting, because no one else is going to mimic that stunt, because he rotated, he basically, you're just on the verge of death for a very short portion of his jump, but he pulled it out, which is amazing. Okay, so hell yeah. So that's why we can also just solve for, hey, I just want my acceleration, so let's do that. Acceleration, bring this downstairs, cancel the masses, is a gravitational constant, mass of the Earth, radius big squared. Cool. So I can solve either one of those. So let's do that. Let's say the force of gravity is 1 Newton is equal to the mass of 1 kilogram, mass of the Earth, divided by radius big squared. Cool. And then we'll also have the acceleration of 1 meter per second squared is equal to gravitational constant, mass of the Earth, divided by radius big. Cool. So, like, this is for me jumping off the cliff. I want to experience 1 meter per second, but I also want to set up the scenario where, what does this say? This says if we have that 1 kilogram jumping off that same height, it's only going to experience a force of 1 Newton. So we go back to, like, you know what I mean? We have our 1 kilonewton, 2.2 pound chunk of whatever. And then we have that little fish scaly thing that I can put, then I can generate a force. You know what I mean? I can push into this, and then just make sure the fish scale only says, you know what I mean? Well, what would it say? Well, 1 Newton, which is, so 1 Newton, or like 0.25 pounds. And then I want it to go 20 inches, you know what I mean? Or 0.5 meters. So that is the scenario that we could easily do just on a winter's day for free, or we could do the same thing by trying to make a huge tower. And if we ever got the space elevator, you could you could have some fun at that zone, you know what I mean, and play around with that gravity for a longer time. Or try to pay someone big bucks to fly you to that zone, and then you could do those same experiments. Okay, hell yeah. Alright, hell yeah. Now, you know what I mean, it's part of the video where we actually get to solve our first thing. You know, we will definitely get back to why we don't crash in the sun as a finish. But once we solve this, then we can actually solve this question, why don't we crash into the sun? So, hell yeah. So we're just going to do this one. We're going to say we need to rearrange and solve for RB. You know what I mean? So let's do this just in one step. We're going to bring the 1 Newton downstairs, or the force of gravity. Well, I guess we'll do this in a few steps. So we bring radius big upstairs. We'll still square it. That's going to equal to gravitational constant, our mass. I apologize. Like, we want to do this just 1 kilogram. So we built the huge tower, and we got a 1 kilogram mass. All right, and then divided by, so we already brought the radius big squared up, and then so force of gravity comes down. Cool. So now, but in our equation, we want force of gravity to be 1 Newton, so we know what that is. We know gravitational constant, that's 666 times 10 to the negative 11. This is 6 times 10 to the 24. Cool, and this is 1. And then so we basically know everything, but we just want to solve for radius big. So we're going to go radius big is equal to the square root of and now let's write this. Well, I guess we'll do it like this: GMME divided by force of gravity. So at least now you see it, and let's figure out what the units of gravitational constant are, just so you believe me. So we have radius big is equal to the square root of 6.67 times 10 to the, yeah, you could just say 666. But then if you know it's 6.67, ooh, you get hella close. We'll leave room for the units. We're going to multiply that by 1 kilogram. Mass of the Earth is 5.9? Is it 5.9? 5.9. Oh, 5.94 times 10 to the 6. You know, who cares? It's 6 times 10 to the 6. And then we're going to divide by 1 Newton. Okay, and then anytime you're trying to figure out units, definitely write F equals MA, and write 1 Newton is equal to 1 kilogram, 1 kilogram, 1 meter per second squared. Because now I see newtons. So what, oh, bummer, dude. I need to get kilograms on that. Sorry I write it so small. And so and so we have kilograms times kilograms. We have the units on this. Let's get this to be 1, so all we're doing is converting the units of newtons to kilogram meter per second squared. So this is going to be 1 kilogram divided by, oh, I apologize. No, kilograms multiplied by meter per second squared. All right, so one of these kilograms cancel. Now we have to. So that's it. All we have is meters per second squared downstairs, a kilogram upstairs, and now we need to make sure this is balanced. And at the end of the day, we need to get meters out here. And because this is in the square root, we have to at the end have this to be meters squared, and then the square root of that. So everything in here has to be meters squared. So these are cool, like, first chapter physics problems that they do melt your mind, man. You got to spend some time. And then we even have a meters downstairs. Like, that's not helping. You know what I mean? So if we actually take stuff to the top, we're going to have meters to the negative 1 upstairs. Now this is dividing by a fraction of meters per second squared. And if we divide by that, that's the same thing as multiplying the top by the inverse. So second squared divided by meters. And meters downstairs is the same thing as just saying second squared is meters to the negative 1. So that's what I'm kind of doing all in one step. I'm saying, hey, meters to the negative 1 is upstairs. And then we just have second squared. And then we also have that kilogram. And so now what we need meters squared. So this has to be meters cubed. And you're like, whoa, never knew that. That sounds bizarre. But this will cancel one of these and we'll be left with meters squared. But this also has to be seconds to the -2 because it has to equally cancel that one. And this has to be kilograms to the -1. All right, hell yeah. So the gravitational constant has to be meters cubed divided by kilograms seconds squared. And there's a few ways to write this. And the other ways to write this is like, well, can't we say that rearrange this? I mean, can't we say that 1 kilogram? And then let's actually rewrite this. So 1 Newton is going to be, and let's just write it without the ones. So we have Newton is equal to kilogram meter seconds to the -2. So if we see something like that, we can convert this to newtons. So what do we have? We have meters cubed, kilograms to the -1, and then seconds to the -2. Well, cool. So we have seconds to the -2, and we have a meter. So now you can, I mean, this is fascinating, but this is just really good skills to develop. And there's, you don't have to have any rhyme or reason for it. But hey, let's say this, so I'm just going to break this up. This is going to be meters squared. And then I have kilograms to the -1. I'm going to have meters seconds to the -2. So see, I just isolated that feature, and I see that feature right here. So let's say newtons divided by kilograms is equal to meter second to the -2. Hell yeah. So now I can actually put that in right here. And so I can say meters squared, kilograms to the -1 is equal to, -1 is equal to Newton. And this is also just newtons to the kilogram to the -1. So we'll have newtons kilogram to the -1. I just didn't want, because this is -1 up top, and then if I divided by a negative kilogram, it might have been confusing, like you could have canceled. But no, these are going to add to Newton meter squared kilograms to the -2. So that's going to be newtons meter squared divided by kilograms squared. So hell yeah. So more things. And if you needed a check on reality, you just try it out. You know what I mean? So let's try this one out. So we have newtons meter squared divided by kilograms. We're going to multiply by kilograms twice. So we're going to go kilograms squared. And cool. And then downstairs, let's just keep with the newtons. We're just going to divide by a newton. Cool. So see, we're on a roll. So those newtons cancel. One of these kilograms cancels one of those. And then we're left with meters squared. See, I might have made a mistake. Yeah. Let's hit the pause button. Oh, this is crazy. You know what I mean? I do like making mistakes, but I just don't like to be on tangents where we're like not getting to the original problem. But yeah, here was my error. I just said that the gravitational constant units was newtons meters squared kilogram divided by kilogram squared, or this. Newton meter squared kilogram to the -2, and then when I wrote it over here, I forgot to write this squared down here. You know what I mean? So if the gravitational constant was Newton meter squared divided by kilogram squared, I multiply by kilogram squared and then divide by Newton. So that's kind of the simplest way. So I would say this is the most logical way to write the gravitational constant, even though, hell, it gets written like this all the time. Meters cubed divided by kilograms second squared, or you know what I mean? And who knows what order you want these in. But this is nice. You have gravitational constant Newton meters squared divided by kilogram squared. Kind of sexy. And then, these 2 kilograms cancel. This Newton downstairs cancels, and you're left with meters squared. We're going to square root that, and we're left with meters. All right, booyah. So now you trust me, hopefully, and let's do this. So sometimes I don't, but 6.67 times 10 to the negative 11. I like to store that in my calculator as G. An alpha E, I don't have it, so 5.94 times 10 to the 24. I like to store that as alpha E for the mass of the Earth. And now we're just good to go. Everything else is 1, and there's no squareds going on in this except the square root. So we're going to go alpha G is the gravitational constant times alpha E, mass of the Earth. That's it. And then the square root of that. So this is our height. And it's this height, don't get it confused with the actual height. It's not this height. It's the radius big. It's the radius. If here's the Earth and this is the tower we want, this is radius big. Now, if we want this height, we have to say this is the radius of the Earth. So we take radius big minus the radius of the Earth, and we're left with that height. So radius big turns out to be, and if you get a big number like this in your calculator, I just like divide by 10 to the 6. Oh, sweet. So now I know it's 19 million. That's the fastest way. That's going to be the fastest way to identify a number in the millions, you know what I mean? And then we're just going to multiply by 10 to the 6 to get it back. But yeah, because you'll have numbers like 33 megapascals, 33.3, and the answer came out like this, 1, 2, 1, 2, 3. And I'm just like, whoa, that's the answer? You know, in pascals, you know, because if I'm doing a material mechanics question, like I don't know how many megapascals that is, but then I just divide by 10 to the 6, oh, it's 33.3 megapascals, cool. And then multiply by 10 to the 6, and then just get a visual understanding that's going to be, 33,300,000 pascals, you know what I mean? So let's go back to our answer, and we found that it's 19,904,723 meters. And I'm going to store that as alpha B for our radius big. Cool. Alpha, and then alpha R? Yeah, so we have alpha R in our calculator is 6,370,000 meters. So now you can see that the height is going to be the difference between these, alpha B minus alpha R. And so, our height is going to be 13,534,723 meters, and the check on reality is to divide this by 1609 meters. If you've ever run track, in high school or whatever, the 1600 meters, that was my race, is a mile, you know what I mean? It was called the 1600. It still is 1600 meters, called the 1600. And but a mile is 1609. But at the end of the day, if you just remember 1600, you can't go wrong. Divided by 1600, cool. Or take that and divide by 1609, and this is pretty darn close. But you're at a height of 8,412 miles. So a jetliner gets 7 miles. So no, you need space shuttles. You need a space shuttle to get up there, or you know what I mean. I just did a video on the space elevator, kind of the intro to the space elevator. It's at 22,000 miles, and that number comes up in the news. I might have said that wrong, you know what I mean, but I think I remember that from my problem. I think I remember that from the news. So it's just good to hear numbers in the news, do a problem so you can get those numbers, and then it kind of solidifies the check on reality, especially when doing problems on a larger scale. All right, so that does it. You'd have to be at that height, to experience that type of gravity, or just get 1 kilogram thing on ice and then, just show it for yourself, videotape it, and then that'd be fast. I want to videotape this at least to go to 2 seconds, and then that's just going to be what you'd experience at that height. I find that interesting. And this whole thing was definitionally 1 meter per second squared, definitionally 1 Newton acting on 1 kilogram, you know what I mean? So these things are synonymous. That's why I just dig on F equals ma, And I think it's just too easy just to go into more complicated problems and not just double down on the easy stuff of asking yourself easy questions and identifying easy relationships. And F equals ma, it's not, and again, it's not force is equal to a constant times ma. It's because we have defined it to be that way. So we define a meter. You know, you could define a meter first, a second first, but then you have to identify a Newton. You have 4 things that you actually have to identify. But if we choose what a meter is, a second is, and a kilogram is, then we have this relationship. A Newton is, and I think those came first. The kilogram came first. Meter second. Those 3 came first before the Newton. Newton is named after Newton. And there you go. A force in newtons is defined by taking that 1 kilogram mass and having a change in velocity of 1 meter per second every second. That's just fascinating. Cool. And so we're going to use that concept now to answer our question, why don't we crash into the sun? Alright, hell yeah. So we're going to answer the question, why don't we crash into the sun? And this is such a brilliant way to analyze this. So we're going to say the sun and the earth have never met. You know what I mean? And we need some numbers on this because, you just pull this off of the internet. The most important thing is speeds, because we know the sun is also going around the Milky Way. And so that's a pretty decent relative speed. You know what I mean? We understand the sun's never going to leave the Milky Way, but it is going to go around the center of that galaxy, and it's going on a speed of 230,000 meters per second. So we have velocity of the sun is equal to 2,300. Did I say that right? 230,000 meters per second. And now we're just going to say the sun and the earth have never met. And so we're going to put the earth up here. And the earth is going to just be totally alone in the galaxy, but go in the opposite direction. So you can just imagine the sun's going one way in the Milky Way, and more or less it's going in a straight line. And then the earth, just out of nowhere, I guess, is just going to be coming the opposite direction. And hey, look, like they're going to be on a collision course, let's say. And so we want to know if they're going to collide. Now, the only parameter for this problem is I'm going to set up the distance between the sun and the earth, those 2 different paths that are crossing, to be the current distance away from the sun and the earth. So you have to look that up, and it's this many meters. And in all these problems, you want to work with kilograms, meters, and seconds. So because the speed of the earth, this is what the Google came up with, a high end of, the speed of the sun going around the Milky Way, 230 kilometers per second. So you got to multiply by 1,000 to get meters per second. Now this, we always want to do in multiples of 3, because look at this. This is a billion, you know what I mean? And then this is, holy Toledo. No, sorry, I meant to say million. But this is a million, that should be obvious. And then so this is a billion. If it was out one more, that would be 1 trillion. So you can also say this is 0.15 trillion. And to write this number, you would probably write it as 150 times 10 to the 6. That's sometimes good standard because you want your numbers to be like 10 to the 3, 10 to the 6, 10 to the 9, because then you're understanding that's 150 million. Because you could say this is 0.15 times 10 to the 9. Now I know it's a tenth of a trillion. Holy Toledo. I'm just messing up 100%. So, no, this is the millions column. This is the billions column. Sorry for saying... No, I was right. No. This is going to be... I messed up right here. This is 150, 9 zeros. So there was my hiccup. So this is 150 billion. Or you could say it's... this would be 10 to the 12. If you go out here to... if you make this 0.15, you're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 0.15 times 10 to the 12, or a tenth of billion. Basically, 0.1 times 10 to the 12 is a tenth of I cannot believe I'm just like this is where I watch my videos and then make sure that I kind of keep up on my errors. I'm trying to think trillion and I'm saying billion. No, this is a tenth of a trillion. Trillion is just a big number, you know what I mean? But cool, millions, billions, and then the next category would be trillion. So a tenth of a trillion, or 150 billion, and I think now we're on the all on the right page. Okay, so we're going to say that distance is going to be 150 billion. So written like this, that would be a million. 3 more zeros, 150 billion meters. All right, and so now this is fascinating. You know what I mean? Should we say holy Toledo? Yeah, I guess we're gonna have to say that the you know, because if these both are going at the same speed, if they're both going, if this is going this speed that way and this is going that speed that way, you know, theoretically they're closing in at double that. So I might just want to double this number and say have the sun be a fixed object. So so we know this. This is just kind of just for our knowledge. I'm going to pin the sun into outer space, and I kind of like this concept of just pinning in things to outer space. You know what I mean? Because hey, that's not moving, but we're going to say the Earth is. And the velocity of the Earth is going to be double this. So it's going to be 460,000 meters per second. All right, hell yeah. So now we need, you know what I mean, some sort of, I think at this point we need to do a simpler problem. I thought, oh, we could just get there pretty easily. But we're going to do a simpler problem. And the simpler problem is, hey, let's still pin the sun. It's not moving. And then we're just going to have the Earth in its current location also not moving, but it's going to be able to move towards the sun. So we're in a universe where, hey, the Earth isn't rotating around the sun. It's just kind of like it would be like on an icy lake, you know what I mean? And so that can just easily move in that direction. And this is mind-blowing because because we've all know that there's a force of gravity. And so let's write that. Force of gravity in this case, or just in the general case, is gravitational constant. The first mass, maybe little m, second mass, big M, divided by the radius between those two masses squared. This usually gets little m, big M, because this is usually the mass of the Earth. But for our case, we have the force of gravity. The force, like, pulling these things together is going to be the gravitational constant. We'll do the mass of the Earth because that's small, little m, E. And then the mass of the sun, big M, S, divided by the radius. And this is the distance. This radius is the distance between the center of the sun to the center of the Earth. And it's just fascinating because I know, and I think I'm just going to neglect, I'm just going to, because I just went online and found out, yeah, we just found that out. That's going to be 150 billion. You know what I mean? So let's throw the radius of the Earth in. That's going to be, no, it's only 6. It's 6,370,000 meters. You know what I mean? So hey, that's pretty tiny. The radius of the sun, that might influence. So I'm actually going to look that up and see if this is the distance from center to center. That would be a fascinating one to easily look up on Wiki. All right, hell yeah, this is so cool because you know what I mean. You ask a question and you just learn something about reality. So you know what I mean. So this was the first thing. The distance, the radius of the sun. If we type that in, it's pretty significant. 695,700,000. You know what I mean. So this goes 150. So if this was 150 billion, it would be 150.7 billion. Cool. But this number is not necessarily the distance from the surface of the sun to the surface of the earth. More accurately, we want to know the distance from the center of the sun to the center of the earth, and we have a term called astronomical unit. I didn't know that, you know what I mean? So, and this is standard, like this length is, but that's going to vary because we know that the earth takes not a circular path around the sun, kind of a wobbly. It might be way out here and then gets close, and then way out there and gets close, and then, you know what I mean? And an asymmetrical path to boot. And so at the closest, this number, the Earth and the Sun, they're either their centers or probably the distances, probably just the distances from surface to surface. But yeah, stuff like that is like you're not going to, I don't know, unless you read the fine print of what these numbers are, like that, I don't know if they actually just took the surface to surface distance or the actual center to center. I imagine center to center. And so 147 billion compared to 152, and then we're kind of just right in that average. 150, you can't go wrong, you know what I mean, because even in one astronomical unit rounds to 150. And so that's what we're going to be using for our problem, and we don't need to know any more, you know what I mean. We don't need to waste any more brain space for too much nonsense. Okay, hell yeah. So now that distance is going to be, we can write it again. 150 billion, just so I don't make a mistake. That's million, that's billion, and that's going to be in meters. So now we're going to do the problem where we're going to throw it into this equation. Cool, so let's do that. Let's find the force. And no, we don't just want to find a force. Like, what the hell would that tell us anyway? Cool, we're just going to actually get a big number in newtons. That's not going to be meaningless. We need to go back to F equals ma. And now we have, and now we're going to do a free body diagram. We're going to chop the Earth out of outer space. So then I'm just going to pin the Earth into, and I just do this, like mentally, I take this mass of the Earth and throw it into the deepest reaches of space, no stars, no other mass around, and no forces, you know what I mean? And then I tie it back to our setup. What do we see when we set up this experiment? So visually, I would see the Earth with a velocity of 0 right at the beginning, and then all of a sudden have some sort of velocity in this direction. So I would identify a change in velocity. So we go to our F equals ma. I've identified what I chopped out of outer space was the Earth. Our free body diagram is the Earth. I do see visually with this experiment that the Earth is changing velocity, at least going from 0 to some other velocity. So I have a check that I will have acceleration. So therefore, I must have a force even at this very instant. So that's why we do like snapshots in time. And the initial, like just even setting up the initial condition, we are going to generate a force. And then I go to my textbooks and be like, what are the known forces in the universe? Well, the big one is, or just the most obvious, since we live on a big chunk of mass, is the force of gravity, being a gravitational constant, two masses, and the distances between those squared. Okay, sweet. So I've identified that. Now, how does that relate to our free body diagram that we chisel into outer space? Well, we observe that it's a mass, and the only way for a chunk of mass, just in deep space, away from everything, the only way for it to move is to have a force. So we're going to say, hey, if we do observe, back to our problem, that it's moving that way, we must have a force right here. And do we have any other forces on here? No. Let's just say we don't have any other forces. So cool. We say that this is the force of gravity. And we identified this is the mass of the Earth. So now from here, we can do our F equals ma. And it's a really simple equation. And I think even at the most basic, it's challenging. But then even when you get a more complicated problem, it just gets to be hell. But it's just really good to do as many of these scenarios as you can. So now over here, this is the force. We're going to say force of gravity is equal to the mass of the Earth and then the observed acceleration. We're going to rearrange this equation and say the acceleration on this Earth, that's what we want to know. We want to know its change in velocity, change in time. It's the definition of acceleration. We bring the mass of the Earth downstairs. We got the force of gravity divided by the mass of the Earth. So now we know this force of gravity is this equation. Let's throw it in. And I'm just going to write it over here just so it looks nice. The acceleration is going to be gravitational constant, mass of the Earth, mass of the Sun, divided by, and then I'm going to go radius AU, because this is an astronomical unit. I think that's a very good term, because then you can really see that, hey, our radius is a distance of AU. Sometimes calling this a radius also sucks, because it seems like, well, it must be the radius of the Earth, it must be the radius of the Sun. No, we're talking about the total distance between. Now, sure, if it's rotating around a circle, that distance is still a radius of an arc. But so there we go. Radius in astronomical units squared, and hell yeah, if you want that exact number, this is from Wiki. This is the exact number for astronomical units: 149.6 billion meters. All right, booyah. And so that was the force of gravity part. You know what I mean? So we kind of, that was the force of gravity part. Then we still have to divide it by the mass of the Earth part. So maybe I'll just do it right down here. You know what I mean? And then so, but I think you see it, mass of the Earth cancels, and now we have acceleration is just the gravitational constant, mass of the Sun divided by the radius in astronomical units. That's the distance between the Earth, excuse me, and the Sun. Okay, so now we now we know the change in velocity, and this is cool because we're going to use this, and it's going to explain a concept that where even if you don't know integration, you can set up problems and still make them simple and get an answer. And so yeah, this is going to be fantastic. So let's do it. Let's do it 100%. So we have 6.67 times 10 to the negative 11. Now even right now, I know what we're canceling. Gravitational constant. Ooh, this one I don't. I apologize. You know what I mean? Yeah, not written like this. Written like this, the gravitational constant. Oh, no. I'm just, forget the units. We don't want to slow this video down. We already did the units on this, so we're just going to leave everything unitless and just assume that we're not going to make any mistakes. So the mass of the Sun, this came in. I'm sorry I didn't put it down here. So we got the mass of the Sun is 2 times 10 to the 30 kilograms. Now that's another number that you could probably memorize, at least the 30 part. That's the check on reality. If you got that wrong, there's no reason memorizing anything else. If you just say 10 to the 30, hell yeah. And then, yeah, 10 to the 30. The 2 is meaningless. You know what I mean? It doubles the mass that you thought it was, but you would just be astronomically off if you're starting to go in any other direction, like 10 to the 29 or 10 to the 31. So anyway, so we got mass of the Sun is 2 times 10 to the 30. Cool. And then we're going to divide by the radius in astronomical units. We're just going to round this puppy. You know what I mean? 150 billion. Cool. And at some point, I'll probably just write this 150 times 10 to the 9. There you go. That's 150 billion meters. Okay, because we are going to square that, and it makes sense to do that. You know what I mean? Because 150, what's 100 squared? Well, that's 1, and then 4, that's going to be 10,000. You know what I mean? So we have something that's, maybe like 20,000 times 10 to the 18. You know what I mean? So that's where that would go. Or we can just do it in our calculator. So we got 6.67 times 10 to the negative 11. Whoa. Negative 11. We're going to multiply that by 2 times 10 to the 30. And then we're going to divide it by, I guess we'll do this, 150 times 10 to the 9. And then we're going to square that. So this is our acceleration. Our acceleration is 0.006. And we're totally going to round this. Well, I can just store it as alpha A in my calculator. But this is meters per second squared. It's 0.006 meters per second. So let's get a check on reality. In 1 second, it's going to go 0.006 meters. How far is that? What's this in millimeters? Multiply by 1,000. Oh, well, this is 6 millimeters per second. Okay, now that might not seem very much at all. And so, so now the question is, how many years? That's the first question. Like, the check on reality, on the low end, is when is the Earth going to hit the sun? Now, and I have to throw a huge, huge asterisk here, that this isn't when the Earth is going to hit the sun. The Earth is actually going to go away from the sun. The Earth is moving away from the sun. That's the current trajectory. Because its velocity is faster. That's kind of what we're getting to. Like, the velocity of the Earth is just fast, so it's getting farther and farther away. The sun will die and then engulf the Earth at some point, just because it's getting larger, and that rate will engulf the Earth at some point. But the Earth will never just ram into the sun, and I think that's a very fascinating one, because we're always taught that if you have two masses, there's going to be an attractive force between them, and then that force... and especially if you're learning F equals ma, you're like, well, isn't there a force? And doesn't that cause a change in velocity? You know what I mean? Sure. The short answer is that you have rotation. And I'm not even gonna say anything, because that's where it's just like, that's why I'm making this video, actually, because I want the easy layup in the end to get it. So yeah, I'm coming from the perspective where it's just like, yeah, I can't tell you exactly why, but I can say that all of the force of gravity, like all of the acceleration, is in the normal direction. It's just trying to. We've talked about this before, where if you have an object on a circular path, it has to have a force in the direction of the center. It has to have a force towards the center of the circle to stay on that ride, given a tangential velocity, or that's also saying an angular velocity. Whatever the angular velocity is, and if you're a mass, the only way to stay on that ride is to have a force in that direction. So yeah, so that is the short answer. Like, I can give you that the force of the gravity of the Earth and the Sun, because we are spinning around that circle. The only way to stay on target with that circle is to have a force in the direction, because we want to just move tangentially, but if we did, we would have to get back towards the center. And it doesn't look like it, it just looks like that way. But on a very small scale, we got to move towards the center. And the short, quick answer is, if we're moving tangentially, we have no velocity towards the center. But then a second later, that circle's over here, and we're still on the circle. Why? Because we must have had a velocity towards the center. And if we have a change in velocity, 0 meters per second towards the center, and then some meters per second towards the center, well, hell yeah, that's the definition of acceleration. Change in velocity, change in time, in the direction of the center of the circle. That's acceleration normal, and normal acceleration is r omega squared. So that's where that comes from. And from the F equals ma perspective, F equals ma, your acceleration is the normal acceleration. So then the force is the force of gravity. And so, hey, look at this. So you can be like, well, what's the normal acceleration? You could do the force of gravity divided by mass. And if you did this with Kepler, you know what I mean? That's going to get you this equation. That's going to get you this 0.006 meters per second. And this is cool. I think we can now actually just spell this one out before we do our problem, because verbally I just said it. So we're going to say, yeah, so this is what we just solved for. We solved for the acceleration. But we also know that acceleration is r omega squared. So let's set this up. We got 0.006, or a in our calculator, is equal to the radius between them. That's going to be r ua. You know what I mean? That's going to be that 150 billion meters. And then the omega. How in seconds, how long does the Earth take to go a full circle around the sun? And it is just kind of fun, because you know what I mean? This is why we teach science to kids at such a young age, because they're just like, yeah, they can remember these things. You know, it's 365.25 days. You know what I mean? Because of leap year, you know what I mean, you got 0.25. So let's do factor label method on that. just so we can kind of slow it down a little bit. So we have 365.25 days. We have 1 day is 24 hours. And then we have, I just like, let's just get this done. 1 hour is 3,600 seconds. That's just a good one to memorize. Obviously, it's 60 minutes times 60 seconds, 3,600. So we have 365.25 times 24 hours times 3,600. I feel like I did not do that right. Oh. No, I did it right. That's the seconds in a year. I always did the seconds in a day, 24 times 36,000. I haven't done astronomical problems for a while. Yeah, this 86,000 seconds, that's my check on reality. 86,000 seconds is a day. I have not done astronomical problems, so let's take that big number, divide by 10 to the 6. Hey, it's 31 million seconds, you know what I mean? So we have, and I'm going to store that as alpha t. So we have that time, you know what I mean? For one rate, for one full circle, is 31,557,600 seconds. Cool, and that's yeah, there you go. So that's the time for one revolution, and I'm just going to say for one revolution, because now this is where the problem sucks. Is you have to know what angular velocity is. Its units is radians per second. No one knows what a radian is. So yeah, you have to draw a circle. Draw a radius. Cut a string to that length. And then start draping the... Let's smooth this out. Smooth it out. Drape the string around the circle. You'll probably get to about there. And then you can kind of see that you can get about six times around a circle. It's 6.28. That's 2 pi. But that's the definition. Once you drape that radius, that length, to that location, then you draw an angle. And this is the definition of 1 radian. Cool. And so there's 6.28 radians in is equal to 1 revolution. So factor label method, always write it like this, stack them. 6.28 radians divided by 1 revolution, because now you can use it in a factor label way and then cancel revolutions for radians. Cool. And then let's do this 100%. You know what I mean? So because we want the omega. Hey, this is spinning that way. Let's say, I don't know. It's probably not. It's probably spinning the other way. But the Earth is spinning counterclockwise. So if we're looking at a top, I don't know, top-down view is probably spinning. Anyway, who cares? But we want to get this in radians per second, and so how do we do that? Well, we first need to know how maybe yeah, that is fascinating. How that's kind of well, you know what I mean? It's mind-numbing. So I think we need no, I think we can do this. Oh yeah, so you know, my game plan on radians is like, you know what I mean, I say radians times radius is something normal. And that's the first one. You get S, or arc length. So this length right there, S, is equal to radians times radius. And if we have a radian of 1, the arc length is just going to equal our radius. Cool. And so so how do we do this equation in reverse? So let's do that. So we have radians times radius is arc length. But I just don't think you're ever going to memorize that equation. It doesn't look good. It looks too simple, and it just doesn't pop. But if you just spell it out, radians times radius is something normal, and that's arc length. And that's why I think we should spell out the other two, because we have radians per second times radius is something normal, and that something normal is tangential velocity. And then the third one is radians per second squared, angular acceleration, or alpha, and this is omega, and this is r, times radius is just the acceleration of that, but in the tangential direction. Cool. All right, so now we can see that radians per second is going to be that angle divided by time. Cool. So if we know how many angles we're doing, in the amount of time, that's going to be radians per second. So if we take this equation for angle, that's going to be arc length divided by radius. Cool. And maybe this is the confusing way, because even right now it's just like, no, this is getting just a little bit heady. So let's grab a fresh sheet of paper, and we got radians per second, and we want to know that. And so what I like to do, you at least need to know the circumference. So let's do the circumference of this is going to be like a 2 pi r. You know what I mean? Circumference is also pi d, but it's also 2 pi r. And in our case, this is going to be 2 pi, and then the radius is that astronomical unit. Okay, that's the circumference. Cool. And then that's going to be and this going to get an answer in meters. So we might as well do that. It's going to be 2 pi times 150 times 10 to the 9 meters, 150 billion. So 2 pi times 150 times 10 to the 9. And I'm going to store this as alpha c. This is the circumference in meters, and it's I'm just going to divide by 10 to the 9. Cool. It's going to be 952.5 times 10 to the 9 meters. Cool. So 140 billion meters. That's the circumference. What do we know about that? That's 1 revolution. Cool. And even right now, getting to 1 revolution, then you can be like, well, don't we know that 1 revolution is 6 radians? 6 radians in 1 revolution. You know what I mean? And so don't even remember it as 6.28. And for sure, don't remember it as 2 pi radians. That'll just melt your mind. But from the guessing perspective, just from the, hey, like what's the circumference of a tree? Go to the redwoods, how many people can you get around a tree arm's length? Well, let's just eyeball the diameter times 3. No one breaks out their calculator or their skills of memorizing the digits of pi. It's useless. You know what I mean? So in this case, it's also useless. So if I have this many, if and even I can just spell it out. If this is almost if this is 100 billion, we almost have 1 trillion. So 1 times 10 to the 12. We almost have 1 trillion meters. How many radians is that? You know what I mean? Well, isn't there 6 radians in a circle? And this is the circumference. So look at that. Like this is probably the most mind-blowing part of this whole video. It is for me, because it's just like if you don't simplify numbers, you're just going to lose your skull, and you're never going to catch mistakes at all. You know what I mean? You really have to have a who cares approach. Get that just like, who cares? You know what I mean? So this is a circumference, trillion meters. And that's going to be 1 revolution of the Earth going around the sun, 1 year, right? And so how many radians is that? We just said there's 6 radians in a circle. And I'm literally not telling this for you. I'm literally saying the words so they seep into my brain. You know what I mean? And then just so I can get there faster the next time. I can already know these. I don't have to write down the assumption and then say, hey, guess. You know what I mean? Asterisk, asterisk, asterisk. Guess 6. And so, yes, I think we spelled it out. There's 6 trillion. 6 times 10 to the 12 trillion radians. You know what I mean? That is so meaningless. Like, it is total meaningless to me. If this was degrees, I would be like, yeah, cool. You know what I mean? If I said this, how many degrees is that? 360 trillion degrees. I don't know. I just, for whatever reason, I'm just like, sweet. You know what I mean? It looks like we're going around that thing. No, wait, what are we doing? Is that even true? Oh shoot. I think what I'm saying is just totally dumb. Like, obviously a circle is just still 6 radians. So my bad. I am just getting 2 things hella confused, so you can just erase the last 10 minutes of this video. This is fascinating to me. No. There's only 6 radians in. I'm glad I went to degrees because that made no sense. 360 trillion degrees. Well, it looks like you're going around a circle a trillion times. So I'm glad I did this because degrees. We all know what the hell a degree is. We all know that Shaun White does 360s and more snowboarding. You know what I mean? So that's the mental image that I have in my mind of what a 360 is and how many degrees are in a circle. But I'm so glad I did this because I caught my mistake. If you're going around a circle, there's still 6 radians in that circle. So it's just fascinating. What the hell was I trying to get to? We're trying to get to radians per second. And this is fascinating. Let's go back to our thing that if we have let's go radians times radius. I'm just going to see if my juice even works for myself. You know what I mean? It is arc length. And then we're saying radians, it is the arc length. And then we're saying 6 radians times the radius is the circumference. Cool. And so we know 2 pi times the radius is the circumference. Cool. So, this is fascinating. It's fascinating because, like, maybe we don't even need meters. I'm going to turn off the camera because I need to reset just for a second. Alright, hell yeah. So I took a little break, and, that was so smart because, you know what I mean? One thing you need to know is that the Earth just spins hella slow. So, you know what I mean? If this is 1 radian, I think we got that far. Now, what's an angular velocity of 1 radian per second? Now, these are kind of like visual proofs, you know what I mean? So I'm just going to start here on my circle and go 0, 1. You know what I mean? 0, 1, 2, 3, 4, 5, 6.28. Cool. And so I guess I just should remember 2 pi radians in a circle, you know what I mean? But I wouldn't say 2 pi radians in a circle. I would like to think of it 2 pi radians for 1 revolution, and still maybe say of a circle. But this is going to be our I even wrote it down here, but for whatever reason, it just didn't stick. But yeah, because it's a conversion factor, but this still doesn't help you. But just the visualness of like, okay, if I have a circle and I'm going 0, 1, that's 1 radian. So what we find, and let's like spin the Earth. The Earth is going to spin once from here to there. This is the North Pole looking down on the Earth. It's going to take 24 hours, 86,000 seconds. So now, how long is it going to take to go 1 radian? You know what I mean? How many radians per second are we going? Well, we're not even going 1 radian per second. You know what I mean? Because if we spun that, so we're literally, it would take, you would just have to wait, well, there's 6 of them, so you'd go 24 hours divided by 6. I would have to hold my pencil here for 4 hours just slowly getting to that line. You know what I mean? And then going around the sun, but this is crazy. You know what I mean? So like half of it is, you have 4 seasons. So if I do, like right now it's like end of summer. If I go from right now through till winter, I'll move to there, and it'll be just less than a full season to go 1 radian. And so the number that we're getting is just going to be really small for the and the check on reality for the angular velocity of the Earth. It's going to be that 86,000 seconds. And so now how would we do that? What's the radians, radians per second? Well, we don't know what 1 radian is, but we know that 2.2 pi, or 6.28 radians, I guess we'll do it as 2 pi, 2 pi radians is going to take 86,000 seconds. You know what I mean? So that was, so yeah. In this calculation, I apologize. Circumference did not come up at all. So that was a huge error on my part. But if we go this 2 pi divided by 86,000, yeah, this I think it's kind of an ugly number, but it just kind of, I just think it's weird. You know, it's 7.3 times 10 to the negative 5. I can probably remember that, like 357, you know what I mean? It's 7.3 times 10 to the negative 5. But that's the radians per second of the Earth. It's just a very small number. It's 0.123, 4 zeros, a 7, and a 3. That's how many radians per second that you're moving. You add all those up for the Earth, and it takes 4 hours to go 1 radian. So it's going to be even more astronomical. So the radians of the Earth around the Sun, we'll just say the angular velocity of the Earth going around the Sun is going to be 2 pi radians divided by that alpha t in our calculator of times 10 to the 6, stored as alpha t. And let's do a quick check on this. It's 365.25 times 24 times 3,600. Cool. And that's going to be 31,557 times 600. And again, this was 365.25 days times 24 hours times 3,600. I would never write it like this. I apologize that I'm even writing like this. That is definitely not helpful. The factor label method, I don't know where I actually wrote it. But yeah. I would never write it like that. I would say, hey, there's 24 hours in one day, and then there's 1 hour. So that's how I would for sure write it. You definitely need to do the factor label method where you can cancel your units, and then just so you don't get confused with that. Alright, so we're going to 2 pi divided by that answer. And heck yeah, we're going to store this as W in our calculator, but we have 1.99. Oh, this is pretty cool. It's basically 2. I'm just going to call it 2 times 10 to the negative 7 radians per second. So it's a lot lower than that, you know what I mean? So it's that divided by or 7.3 times 10 to the negative 5 divided by that answer. You know, it's 360. That makes sense. Times slower than. Oh no, I guess it doesn't. Like the radius that our spin in radians per second, our angular velocity. I don't think it's relevant to the actual angular velocity, but it's just fascinating. Let me do that again. Just the difference was 366 times. We're spinning 366 times faster than the us going around the sun. So we think and the spin of the Earth is hella slow. You have to get that into your mind. But the Earth spinning or the Earth traveling around the sun, that is hella slow. All right, holy Toledo! I apologize for kind of messing up, but what we were doing is we identified that the acceleration was 0.006 meters per second, and we have this and we know that was the acceleration, the force of gravity divided by the mass, that side. But we also just know from our textbooks that the acceleration to stay on this ride requires a force, and that acceleration, the normal acceleration to stay on a circle is r omega squared. So we just found our omega, and then we know our r is the astronomical units. So we're going to go 150 times 10 to the 9. That's an astronomical unit, or averaging it, or I mean just rounding it. And then we're going to go alpha or omega squared. Cool. And so that angular acceleration is 0.0059, 4624, and it's the same. You know what I mean? So alpha A. Look at those. You know what I mean? So that's fascinating. Look how very similar the angular accelerations are. And they say that we are not moving towards the sun, but moving away. But just that quick calculation has the force, the acceleration due to gravity. Oh, no. So even just this actually spells it out. So in my calculator, alpha A was this number, 0.00592. It was lower. That was the acceleration due to the force of gravity. And, like due to it. So that was F equals ma. You can't do this enough. That's force of gravity times the mass that we're trying to do, the Earth, and its acceleration. And we said that the acceleration was that force of gravity, that Kepler equation divided by mass. The masses cancel, and we did that. And that was the acceleration due to the gravitational force with the Kepler equation. And that's going to be lower than the acceleration needed to stay on our current path around the sun. If we want to spin around the sun on that circle, it requires, to ride that ride, you must have a centripetal force towards the center. If this is the mass, you have to shove it towards the center of the circle if it's spinning with a angular speed. The only way to stay on that circle, and the higher this angular speed, the more force is going to be required on that mass to stay on that ride. And then we found that ride requires requires more force. Cool. That ride requires 0.00594, almost 0.00595 to ride, where the acceleration due to gravity is 0.00593. You know what I mean? So those are your differences, and that's kind of a mind-blowing part. 595 and 0.00593. So the difference in that acceleration is why we are moving away from the Earth. It doesn't matter. I don't think we're moving away very fast from the literature, and the sun's going to engulf us anyway. All right, so cool. I'm going to take my first break because now what we're going to do is we have found that we're moving 6 millimeters towards the sun, and I want to know how many years or days, or just get some time frame on that. But we know that's not going to be the case. So, and why is that not going to be the case? Because if we get closer to the sun, the Kepler's equation of gravity is going to be a bigger force. A bigger force, F equals ma, means our mass hasn't changed, so we have more change in velocity. So if every second goes by, and this is fascinating, getting it down to base units, every second we're going to be 6 millimeters closer to the sun, even though it's hella far away. You know what I mean? Hey, there's a lot of time to kill, and I guess the take-home point here that's really should be stated, it might not be obvious, but if we get half the distance away, our acceleration doesn't double, but it's a factor of 4. You know what I mean? And I think that's fascinating. And from the standpoint that it's not exponential. You know what I mean? It is, well, I guess that's the definition of like it's not like logarithmic. You know what I mean? It's not on a logarithmic scale where if you well, even that, I guess it's exponential, but it's only by an exponent of squared. And so you get halfway to the sun, this just goes, instead of 6 millimeters a day, you're going 12. So at that point, it's just like, well, who cares? And that's what I'm going to show after I take a little break, is like, hey, we're going 0 meters per second to 60, miles per hour. So that same car, and you're trying to find how far we're going to go and how fast we're going to, basically what's our average velocity, and then how far we can go. So the same thing here. If at halfway we're only going 0.012 meters per second or 12 millimeters per second, cool. It looks like our average velocity is just the halfway between those, and that's going to be 8 millimeters per second. Okay, so if we're going 8 millimeters per second for half that distance, then that's how long that's going to take, and we can reset the problem. Now we can say we're here going 12, and then we're going to go get to a quarter of the distance. You know what I mean? Well, what's going to happen? Oh, and my bad. See, I'm already making mistakes. I just said that our acceleration is going to be a factor of 4. We half the distance, we do a factor of 4, and then so this would go 6 6 times 4 is 24. We'd go 0.024 meters per second, 24 millimeters. Halfway between these two numbers, well, you have to use the equation of like 24 plus 6 divided by 2. That's going to be the halfway equation. You know what I mean? That's definitely something you want in your pocketbook. That's going to be 30 divided by 2 is 15. So our average velocity for half the distance is going to be 15 millimeters per second. So now you can actually figure a time value on that. How long is that going to take? And then you can say go go to a quarter of the distance. So at half the distance, this is our acceleration. At a quarter of a distance, we're going to be 4 times 24. If this was 25, that'd be 100, but else it's 96. So we're going to be 96, or I should do it like this, 0.096 meters per second, or 96 millimeters per second. And then our average velocity between 96 and 24 for that ride right there is going to be halfway. So we do that 96 plus 96 plus 24 divided by 2. So we have 108 millimeters per second. So then that's going to be our average velocity. Is 108 meters per second. And again, we're just taking our initial acceleration and saying, hey, let's take our acceleration there and our acceleration at the halfway point, and we're just going to say our velocity average is the difference. And that's 100%. Oh no, it's not exact. For some things, it is exact when you're like jumping off a cliff. But here it's just an estimate. Because as we get closer, our acceleration is a factor of the radius squared, but this is a good way to guesstimate. So let me just do a rough guesstimate on this, Whoa. No, we need to slow down. So we're going to do this process just a little bit slower. And then, yeah, we're going to get a time value. You know, maybe we should do years. I think that would be a pretty good time value of when we're going to crash into the sun, since if in the case where we're not rotating around the sun. All right, hell yeah. So we're back. And, yeah, this is going to be a pretty cool part of this, because we have an acceleration of 0.006 meters. Now we're not going to do anything in millimeters anymore. We're just going to stick with meters, and this is meters per second squared. And again, that's going to be a change in velocity of 0.006 meters per second, because that's what we're interested in. We want to know the change in velocity, and then a change in time of 1 second. You know what I mean? So for every 1 second, that's going to be our change in velocity. And we're going to say, hey, we start with a velocity initial of 0, and so our distance is going to be 150 billion meters, and I guess I just have to write it like this: 150 times 10 to the 9 meters. All right, so this is going to be, so in the first second, we're going to go from 0 to 0.06 meters per second. And then after that, we're in the yeah, let's get our equation, because let's see if I'm making any mistakes. So we have F, we're going to say F equals ma. We know that the driving force is going to be gravity. And we can say the force of gravity is gravitational constant. The two masses radius squared. And then we're going to say acceleration is force of gravity divided by mass. But we know that that mass that we're analyzing is the Earth. That comes up twice. This is the mass of the Sun. So we can say that the acceleration is gravitational constant, mass of the Sun divided by the radius. And that's the astronomical units. Well, and in this case, now it's just going to be the distance between the Earth and the Sun, and it's going to change. You know what I mean? So that value is going to change, and that's going to be our new acceleration. So let's get some checks on reality, and then throw in the halfway point. The halfway point is going to be 6.67 times 10 to the negative 11. Mass of the Sun is 2 times 10 to the 30, And then the radius of the Earth, if we half this, is going to be 75 times 10 to the 9. So let's throw this into our calculator. And what are we assuming it's going to be? Well, we're getting closer. Oh, I'm sorry. This has got to be squared. This number isn't so large as it was in our initial. And so we're assuming that this is going to go from 0.006 times 4. So to 0.024 meters per second squared. And let's try it out. 6.67 times 10 to the negative 11, 2 times 10 to the 30, divided by 75 times 10 to the 9, and then I definitely got to make sure to square it. Hell yeah, and we get 0.0237, you know what I mean? So I'm just going to, so now we know we have a check on this equation, and then we go a quarter of the distance. Well, it's going to be 4 times that, 0.024 times 4, and we're going to be at 0.096 meters per second squared. Okay, heck yeah. See, I'm so glad I did this, because before getting a fresh sheet of paper, we were just making horrible assumptions. You know, that was kind of messing with my mind. I said this was going to be velocity. After 1 second, sure, you're going to go 0.006 meters per second. But then I said at the halfway point, you're just going to go 4 times that. No, that's nonsense. This is your change in velocity for every second. What you can do, because this is just one of those problems where, hey, your acceleration due to the force of gravity isn't going to be constant anymore. At the halfway point, the acceleration is going to be 0.024. You know what I mean? So let's circle both these. And so now here is you can, it's not a true statement, but at least we can be like, well, let's just average them. You know what I mean? And so let's do that. So 0.024 plus 0.006. And then divide by 2. That's how you average those. So for the first half of our trip, we're going to have an acceleration of 0.015 meters per second squared. Now that's not going to be the actual. You would need to use an integration approach to figure out what the actual average acceleration between here and there is. But we're just taking it to be linear, and it's not. You know what I mean? Because if we go just not half the distance, but just a quarter of the distance, well, then we're going to be at 0.0. Then we're going to be at a half. Yeah, and let's do that. You know what I mean? So let's do that and see what error we would have, or if it is true. So halfway between 0.006 and 0.0012 is 0.008, and then halfway between 12 and 24 is 12 plus 24 divided by 2 is going to be 18, so 0.0018. Okay, so now we're saying, hey, we're going to be, our average for the first quarter of this trip is going to be that, and the second quarter of the trip is going to be that. Let's average these. So we have 0.008 plus 0.018 divided by 2, and we get 0.013. So actually, this is a better average for our acceleration than 0.015. And I think that's the case. I think because we have another check on reality of that the quarter of the way is 0.002, that we get a more accurate answer. And if I wanted to do it even more accurate, just go 1/8 of the way, and then oh, you know what? I feel like I did another error here. You know what I mean? I don't think this was right. I think this should have came out maybe more, actually. But you know, the distance right there probably isn't 0.012. So if I say this whole distance, got to get it down here, is 150. Halfway is 75. Then this is 35. So that distance is going to be 75 plus 35. So that'd be 75 plus 35. That's 110. I can go back to my equation and then throw it in. You know what I mean? So now I can throw in 110 for the radius, and we get 11. You know what I mean? 0.011, not halfway. So, okay, yeah, so fair enough. So maybe this was a good representation. But anyway, so that aside, sure, you can get super technical with it, but we're just trying to get just a quick average. So for the first half of the journey, our change in velocity is going to be 0.015 meters per second for every second. So now what we can do is get a oh, this is interesting. I swear I got to go back to this driving car, 0 to 60 miles per hour. And I'm going to drive for a half an hour. My average speed is going to be 30 miles per hour, and I'm going to go a distance of 30 miles. So from here, because this is part of our problem, our velocity initial is 0. Our velocity at this some halfway point is going to be, well, the time to get to that halfway point, you know what I mean? And so the time to get to that halfway point, we don't know, but it's going to be that. And if we did know that, oh man, yeah, this is an interesting one working backwards. I mean, you would just want to use the kinematic equations, but we can do this working backwards. We can say well, let's go through it forwards and then see what we need and see if we can come up with an equation from this. I know I'm traveling 0 miles per hour, and at some point at the halfway point, I'm going to be traveling 60 miles per hour. And then my diagram says I know I'm going to do that for a half of an hour. And then I know the average velocity is the difference between these. I'm going to say this is V max, but if I'm starting at 0, I know my average velocity is just V max divided by 2. Cool. And I kind of want to know my average velocity. And oh, in here, I think we need an acceleration term. Acceleration is change in velocity, change in time. What's my change in velocity? Well, 60 miles per hour, and my change in time is a half an hour. So, oh, I never thought to actually use an acceleration on this. So we have 60 divided by 0.5, and my acceleration is a change in velocity of 120 miles per hour for every 1 hour that I'm traveling. Okay, hell yeah. And now I'm going to actually pause because I don't know if I would use this approach to actually get the average velocity or how to just simply get a guess. Alright, but before I take too much time to do that, what we want is the first check on reality. We're saying that in 1 second, our speed is going to increase from 0 to 0.006 meters per second, which is 6 millimeters, which is something. You took the whole Earth and you moved it 6 millimeters. I think that's impressive. So now what we want to do from that, let's just say we have a velocity of 0.06 meters per second. That's where I kind of wanted to go with this problem. I just didn't realize, hey, this happens in 1 second. But cool, we do have some sort of velocity. So this will be the absolute slowest that the Earth will reach the Sun. Just by initiating that acceleration for the first second. And we know that acceleration will actually increase. But just given that, we have this. We have meters per second. And now we want to know, and then we're going to know the distance. And if we know the velocity of the Earth towards the Sun and the distance away of those two, we can use both these and get this time. And so how would we do that? I always do the units as the equation because I want to take distance, divide by meters per second, meters cancels, and time pops upstairs. So cool, I'm going to take that distance of 100, yeah, I guess we do the full distance. So 150 times 10 to the 9 meters divided by 0.006 meters per second. All right, let's do that. 150 times 10 to the 9 divided by 0.006. and we get 2.5 times 10 to the 3 seconds. That's a lot of seconds. Let's divide by 3,600. That's how many hours, divided by 24 hours. That's how many days, divided by 365.25 days. And this is how many years. So it would only take 792,000 years. So let's just do that. 792,000 years. Even if there was a force of gravity that increased, even if that force just acted for 1 second, and the sun and the earth were stationary objects in the universe, it would only take that many years, less than 1 million years, for the earth to crash into the sun. And I think that's a staggering kind of interest. It's very fascinating, because it's the fact that things are moving around a circle, and it gets back to that identity that, like, hey, it's actually hard for things to be captured by other objects. So that's what I'm going to propose the question for myself, is like, if the Earth is coming in like with that velocity at this distance, you know what I mean, how close is it going to get? So for our problem, we might just do like whatever this distance is, maybe start out twice as far away, and then see how far in the Earth actually gets to the sun. And I don't know, just thinking about it, I don't even know if that's a practical question to ask, or if I can even do it. But anyway, we're going to finish with this one, because obviously that acceleration is going to happen over a longer, we're going to increase in velocity for every second. So let's go to the straight kinematics, because if I can't come up with a scenario for this to work, I think we should do the kinematic equations. So what I do is, you know that acceleration is change in velocity, change in time. It's also dv dt. So we can be like dv dt, that's another way to say acceleration, is equal to 0.006. So let's do that. We got dv dt is 0.006. We're going to rearrange variables, integrate. We're going to get an equation for velocity. This is going to be 0.006 times t plus a constant, but at time is equal to 0, our speed is 0. So cool, here's an equation for velocity as a function of time. And we kind of understood that. For every second that goes by, we're going to increase our velocity. But what we're more interested in is just the distance. So we're going to say, so now the next check on reality, this was the worst case. The next check on reality is we're going to be like, hey, let's say this is the acceleration in our starting position, which it is now, and we're just going to say this acceleration is constant. Even as the Earth gets hella close to the sun, we're just going to assume this low amount of acceleration. And so now we get to our next equation. We know that velocity is change in position, change in time. So we write that as dx dt, and we can write this equation. dx dt is equal to 0.006 t. Rearrange variables, get the dt over there, and integrate. So now we have an equation for position is going to be 0.006, this goes t squared, so, and then you got to divide by 2. So we got 0.003 t squared. Kinematic equation is the acceleration divided by 2 times squared plus the initial velocity times t. We don't have that, but we do have a constant. When time is equal to 0, our position we're going to call 0, 2. So heck yeah. So now we have an equation that now we're going to throw in that midpoint. So x, we're going to throw in 75 times 10 to the 9. 75 billion meters. And we're going to get a time frame on that. So that's going to be the time for halfway. And that's what we're going to do in a second, because we're going to assume we're going to break it up into 3 chunks. But right now, I guess we're going to do the full distance, and we're going to figure out the time for that full distance. We rearrange this equation, and we go x divided by 0.003. We square root it, and this is going to be the time and we're going to say the full distance, 150 times 10 to the 9 meters. Okay, hell yeah. So let's throw in that 150. So we got 100. Well, we're going to do the square root. 150 times 10 to the 9 divided by 0.003. Cool, and we get a time divided by 10 to the 6. This crap's happening real fast. You know what I mean? So it's 7 million meters. I mean 7 million seconds. So we have 7.071 you know what I mean seconds. So now we're going to take that number and we're going to divide by 3,600. It's only 2,000 hours. In 2,000 hours, the Earth is for sure ramming into the sun. And that's where this problem just gets very fascinating. You're like, holy Toledo. Rotational dynamics is essential for one, to actually keep two masses to like in an orbit, you know what I mean, with one spinning around another. That's fantastical. And then the other thing is that they won't separate. The fact that they can get caught with each other and not just collide is very fascinating. Cool. So now we're on a roll because it took that many hours divided by 24. It only takes 81 days. 81 days for the Earth to crash into the sun, given its current acceleration, like, you know, right now, you know what I mean? So that's fascinating. But we know if we get to the halfway point using our equation, so we're gonna go back to our equation, and we throw in 75 here, 0.75. Oh, sweet! This is a pretty nice number. Divided by 10 to the 6. It's a whoa. Divided by 10 to the 6. It's a 5 million. So we have 5 million seconds. And divided by 3,600, divided by 24, that's 57 days. So it takes 57 days to get to the halfway point, given this acceleration. But now that's what we're gonna do is we gotta find ways to get a more accurate answer. So we get acceleration of 0.006. So I'm sorry this is so dark. But here's the halfway point, and here's the ends, and we got 0.006. We say at the halfway point we're going to get 0.024. Cool. And then at this third, we're going to get 0.024 times 4. And we're going to get 0.096. And heck yeah. And so what we're going to say is we're going to average these two. So we're going to go 0.024 plus 0.006 divided by 2. And we get 0.015. That's going to be our acceleration for half the distance. And then we're going to have here 0.024 plus 0.096 divided by 2. And we're going to have 0.06 meters per second squared for that part of our journey. And I think it gets complicated, you know what I mean, if you get too close. So let's see. So this is 75, this is 35 divided by 2. I guess let's get close, 17.5. And that's going to be 0.096 times 4, and we're going to get an acceleration of 0.384. For this zone right here, you're going to have that plus 0.096 divided by 2, and you're going to get an acceleration of 0.24. So that's when things get hella fast, and I think it could just be, and then for this final zone, we're just going to say this is our acceleration, 0.4, because things are going to get super hot and heavy. So let's do that. So we know our kinematic equation is and this is interesting because we'll have to integrate at each point. So maybe we bit off more than we can chew. But it's just it's a good example to use the kinematic equations, and that's what we're going to do. All right, so to start off, we're going to have that velocity is 0.015 t. We integrate again, we get position is half that, 0.075 t squared. Cool. And now we can find the time for that. This is why we don't want to bite off more than you can chew. So we might, but we're going to the halfway point. So that's where we say the time for the halfway point is x divided by 0.075 square root, and then we throw in x of 75 times 10 to the 9 meters. So I apologize if I'm just going kind of faster on this. I just kind of want to get some answers and probably move on to the next thing. All right, divided by 0.075. Yep, and so this is going to be the time divided by 10 to the 6. Whoa. All right, that's 1 million. That's 1 million. So our time is 10 to the 6 seconds. All right, at 10 to the 6 seconds, we want to know our velocity at that halfway point. And that's going to be 0.015 times 10 to the 6. That's going to be a velocity of 15,000 meters per second. So now at the halfway point, we're already going 15,000 meters per second. So now, and our new acceleration is going to be that second average. So we're going to have 0.06 is dv dt. We're going to separate variables and integrate. So we're going to get velocity is 0.06 t plus our initial velocity of 15,000 meters per second. Hell yeah. Now we're going to get our position, which is 0.03 t squared plus 15,000 t plus our initial position. We don't have to throw in an x on this because we already just know we're going to be at the halfway point. Cool. So let's try to keep it simple. So now we're going to say, hey, what's the time when this thing is when we travel a quarter of the way? So is that, we have 150, 75, so 35. Oh, well, no, 35.5. 75 divided by 2 is 37. So at 37.5 times 10 to the 9, what's our t? So we set this side equal to 0, and we're going to subtract 37.5 times 10 to the 9. And now, I'm just going to, if you don't want to use quadratic, throw it into your calculator. I hate the quadratic equation. But let's do it both ways, though, since I hate it so much. All right, quadratic equation, and let's just see if we can do it fast as. It says negative b, negative 15,000, plus or minus the square root of b squared, 15,000 squared, minus 4 times 0.03 c, and that's going to be negative 37.5 times 10 to the 9. Cool. All divided by 2 times a, 0.06. All right, let's try that. And so we're going to go negative 15,000 plus the square root of 15,000 squared minus, and screw the minus because we got 2 of them. I hate minus signs. All right, 4 times 0.03 times 37.5 and then divided by 0.06. Okay, so we get a what did this give us? It gave us a time frame of 0.0025, which I think is totally wrong. So I'm going to actually take a break. I hate the quadratic. All right, hell yeah. So we took a little break, and oh my gosh, I had way too many errors. So in my calculator, I had 37.5, and so that's obviously 37. And we'll start out with the plus one, you know what I mean? So, and I got everything divided by 0.004. But just writing the quadratic, I swear I'm going to make one mistake every time. I'm going to, whoa. So insert parentheses, insert times 10 to the 9, and end parentheses, divided by 2a. So we got that, and enter. So cool. And if we want to know the negative root, just to make sure one looks right and the other just looks awful. Okay, yeah. So we have the right one, and we get a time of our time is 89 0.5643 seconds. And I feel like I have an error though, because we said the distance to cover 75 times 10 to the 9 only took a million seconds. So it shouldn't, because we have an initial velocity, you know what I mean, and then our acceleration for that second segment. Shouldn't we be faster? So I'm going to pause the video on that. Alright, hell yeah. So I haven't found my error, but I just went back to this initial acceleration, which we thought was the average between those first two, which was 0.015 meters per second squared. And so we used this equation, and we used it to get halfway. So I used the equation to get to 70. So we went halfway at 75. And then I went 75 plus a quarter of the way, and that's only going to take 1.2 million times 10 to the 6. So we at that speed, our time should only be about 200,000 seconds more, even at that initial acceleration. But now we're saying that our acceleration for the second part is much higher. And so I find that fascinating. So yeah, because we start with the acceleration of the second part to be an average of 0.06. Our velocity equation, 0.06 times our initial speed, which is 1 million into this equation, 0.015. That's going to be our average acceleration for the first part, times 10 to the 6. That speed is 15,000, and so we have that. We integrate for the position. That's acceleration divided by 2, t squared, plus 15,000. And then our, and our constant is 0. We're just saying we're at the halfway point now with that velocity. And so now we just want to go a position of 37.5, or a quarter of the distance, times 10 to the 9. And if we did that, our time values in the quadratic, I hate the quadratic, so we're going to do this. We're still going to say that's our position, given all these parameters. We still got to move that to this side, negative 37.5 times 10 to the 9. But now we can throw this into our calculator. Our time is going to be our x value in our calculator. This is going to be our y, and we're going to go 0.03x squared plus 15,000 x minus 37.5 times 10 to the 9. Okay, now we're gonna graph it. It's not gonna show up in our graph, but we can just do this. We just want a straight line somewhere. So our y, we need an x of like 0 to we think it's going to be within 300,000. So there's just 3 times 10 to the 8, and then our y value. I don't know. We could do 10 to the 6, and then, negative 10 to the 6, 10 to the 6. I'm just guessing. But no. That was dumb. Okay. So our window, we're just going to do our y negative 1 to 1, and then 0 to 300. This is the one we need to vary. So yeah, we can still have this to be, 10 to the 3. Sorry. I shouldn't do that anyway. So this is just the first one. We want to see where our time value pops up. Oh, and I should let it do its thing. Obviously, it's going to come down somewhere at 200,000, hopefully, and it doesn't. Oh, this is wigging me out. So what mistake did I do? The fact that we can type in the quadratic again. Holy Toledo. Yeah, I guess let's start there. So we have negative 15,000 plus the square root 15,000 squared minus 4 times a, which our a is 0.03, times c, which is 37.5 times 10 to the 9. And then that's going to be parentheses all divided by 0.06. That's a, oh shoot, that's a non-real answer. Yeah, it's so what am I doing wrong here? 4 times 35 times 10 to the 9. Alright, I seriously got to take a pause. Sorry about that. Alright, hell yeah. So I found my error. Damn. You know what I mean? And this is where you really just want to, you know, maybe round to just one decimal. But we said our initial acceleration was 0.006. Here's the error. This is just way high, and I can't see that it's high at all. But you know, we start at 0.006 and go to 0.024. The average is 0.015, and so our kinematic equation, half this, is not 0.075, it's 0.0075. So 0.015 divided by 2 is 0.0075. So that means that, yeah, this time is way more than a million. So we have 150 times 10 to the 9 divided by 0.0075. And now we have, divided by 10 to the 6, we have 4. We have 4.5 times 10 to the 6, 4.5 million seconds for that first part. Cool. And now this second part, sure, our quadratic equation was just fine. Well, once we got it kind of sorted out, and I did it a few times and messed up a few times, and my take-home thoughts is like, hey, don't mess with that negative, and if something's negative, don't mess with it, because so that's what we have in here, and I still don't even have 37.5 in here. 0.5, and yeah, so this comes out to be 108.95,643. So cool, we got to check on reality there. We should store these time values, alpha t. Let's store this as alpha s. So now we have a time value that it's going to take, you know, this amount of time to go halfway, and let's figure that what that is. That's alpha t divided by 3,600. That's how many hours divided by 24, so it's 51 days. So we got 51 days to get halfway, and then alpha s divided by those same things, and then we have 10 days. So 51 days to get halfway, 10 days to get the, you know what I mean, 3/4 of the way. Okay, cool. And so at this point, you know what I mean, this is where you don't have to use integration. Like, if I said the Earth was going to reach the sun halfway in 51 days, you could be like, whoa, we're dead by 100 days. You just doubled that. We're dead by 102 days. You know what I mean? And then if I said, well, actually, that's not the case. It's going to get 3/4 of the distance in 61 days. You're like, holy Toledo. So let's redo the problem and say, cool, 51 days is halfway, but then it's going to go 1/4 of the way in 10 days. Well, cool. Isn't it going to reach us in another 10 days? So now we have 51 plus 20. That's 71 days it's going to reach us. And you just stop the problem, you know what I mean, and you got to check on reality. And but I guess we will and our acceleration was 0.06 for that one. What are we gonna average our acceleration? I mean, we should do this again so we don't make mistakes. So so we're gonna go. So we went halfway, 1/4 of the way. We want to go 1/8 of the way. So that's going to be 337.5 divided by 2 plus 112.5. So this is going to be a total distance of 131.25 times 10 to the 9 meters with the average acceleration right there of 0.24. So we use our kinematic equations and we say velocity is going to be 0.24 t plus our initial velocity. So this is where we need to go back to this equation and throw in that, we got to go to this equation, and then throw in this time. So this is alpha s, and then we're going to multiply it by 0.06, and then add it to 15,000. So our new velocity for this next journey, we're starting with an initial velocity of, and I'm going to store that as alpha w, of 68,739 meters per second. So our kinematic equation says, hey, we have to add that right here. Cool. Now we can integrate, separate variables, knowing that this is dx dt, and we can integrate, get an equation for position. That's 0.12 t squared plus that value, which is in our calculator as alpha v, to the t, and we're just going to call that the 0. And then we just know that we have to go 37.5 divided by 2. We're going to go, from here to here, that's going to be 18.75 times 10 to the 9. All right, so now we can do the quadratic, and let's see if we can do the quadratic all in one go. So we have parentheses, negative, this is our b term. I'm just going to do alpha v, plus the square root of alpha v, that's our b term squared, minus 4 times the a term, 0.12, times the c term, that's going to be negative 18.75 times 10 to the 9. All right, we're on a roll. And end parentheses divided by 2 times a, which is 2 times 0.12. Okay, so, damn it. Syntax. Oh, this has got to be a negative. Okay, so now we have a time value there. We're going to store that as alpha r. So we have, it's only going to take that many seconds divided by 300 divided by 24. It's going to take 2 days. So we went from 51, 10, and now to get this eighth of a way, it took 2 days. So to get this last quarter, you can just estimate that it's going to take 4 days. So instead of 51, 10, and 10, it's going to take 51, 10, and 4. And again, we're not doing the calculus on it to find an exact number. We're just trying to find averages. And that's where even taking averages around 2 different locations is plenty. You know what I mean? I'm actually turning this into a little bit of a mess, but it is a good strategy when you're just like, hey, I don't know how to do the calculus, but I can at least get an answer that I'm pretty satisfied with, that's pretty damn close. So then when I do the calculus, I can be like, oh, yeah, no duh, and let's just always do calculus because it just makes it simple. But I don't think so. I think you want to get an intuitive sense for the problem, and I think I'm going to be done knowing that if this took an eighth in 2 days, I'm just going to guess that last thing is going to take 1 day. And I bet you I'm pretty accurate. So 51 plus 10 plus 3. So that's going to be 61, 62, 63, 64. So I'm going to say 64 days. So yeah, but now I'm actually going to have to, sit down with some paper and figure out what the hell the calculus is, because I think everyone's excited, that's still joining me, to figure out, couldn't you just use calculus and find that value, knowing that you have an acceleration, and if you, so we are going to do that. And actually, I don't know if it's going to be complex or simple, but it's going to be fascinating. Alright, hell yeah. So we're back, and we're going to do the integration approach, and so I took a little break and I started writing this down, and it is just so fascinating. My whole goal is to go over the basics so hard that when someone says, hey, you can do it through integration, or do it this, and be like, what are you talking about? Yeah, it goes from the fact that acceleration is dv dt, you know what I mean? We try to use the little carets, you know what I mean? Because those kind of say average velocity, or change in velocity, change in time. Just see if my camera's going. Okay. But then it's just fascinating how, you can take this equation and just throw it into F equals ma right here. So a lot of the more, sophisticated physics textbooks, they'll just write this. And if you don't have a thorough understanding of just always writing it, you know what I mean? I would start writing, acceleration is always change in velocity, change in t, and then do dv dt. Because anytime you see a dv dt, I think most people are just like, nah, thanks. But this is just like, oh, just a change in velocity. I know what that is, change in time. And even though this is supposed to be like an infinitesimally small change in time and then registering some sort of change in velocity, I say, you don't have to think about it like that. It doesn't have to be infinitesimally small. That's almost a nonsensical, because it's like so small it doesn't exist, but it does exist, and then you'll have some sort of change in the velocity. But yeah, even just 1 second, what's my velocity going to change in 1 second? That sounds infinitesimally small, sometimes for problems like this. Cool. All right, so that's why you can kind of throw that value in right there. And then we know that velocity is dx dt. So you're like, holy Toledo. So we can throw, this is an equation, we can throw it in for v right there. And this brings up a point anyway, that anytime you have like a function, like let's say you would have like a function, you would see this, dy dx. You know what I mean? Hey, it's a derivative of the function y with respect to x. You should write it like this, d parentheses y of x dx. See how just even from school days, hey, that's a function. Let's say y is equal to x and this is a function x. We all know what that is. There you go, x, y, and then here's y is equal to x. Cool. So if you write it like this, you're saying that, hey, if I change this x by 1, what does my y change by? Well, it goes from 0 to 1. Oh, no duh. So actually, the derivative of x is going to be 1. So just even doing the basics at a fundamental perspective really help you read textbooks when they do stuff like this. And they'll do it even like like, what do you do? I forget I forget how they do it, but look at these dt terms. These dt terms are totally whole. So definitely downstairs it's dt squared. You can do parentheses here. But here it's the second derivative right there gets the t, not the x. So it's the second derivative of the x. All right, holy Toledo. So then, yeah, so you can throw it into like there, and then, I don't know, it still looks too complex. So let's go back to our equation. We have F equals ma. We have the force of gravity. We did this. And instead of saying radius squared, I was just like, well, let's say it's d squared. And then I was just like, well, I really want to, and that's when I kind of realized, oh, that is my x. So if I have this, this number line, and the Earth is over here, so we're going to kind of go the opposite direction, but we're saying this is 0, 0, and this is halfway, and this is that 150 times 10 to the 9. This is going to be 75 times 10 to the 9 meters. This is going to be 0 meters. And so now what we want to know maybe we don't write it like that. Because do we want to write it as like a function of time? What is our position as a function of time? Because we want to know in 70 days that we're at 150 times 10 to the 9 meters. And then what time is the halfway point? And then we're going to get an equation. Well, isn't it going to take a long time to get here? But then between here and here, it's going to be a very short amount of time. So even right now, we kind of see what our graph is going to be like. Cool. And then hell yeah. So, and I don't know, anytime you're doing like hard integration, you're just like, I don't even know if it's going to be hard or easy. But we took our F equals ma, we threw, and we got our equation right here, gravitational constant, mass of the Earth, mass of the Sun, divided by that distance squared. Because now we throw in, oh, holy Toledo, what's our 0 though? Oh, bummer. Okay, we did this opposite, and I apologize. Well, let's just scratch it out. So here, the Sun is 0. There's 0, and this is 150 times 10 to the 9. So it's just very fascinating because when this is 0, this thing goes to infinity. You're going to have an infinite force upon impact. So obviously this equation will only be useful until we get, you know what I mean. So yeah, definitely keep that in mind. wait, yeah, so our 0 is the center of the sun. Okay, fair enough. Alright, so we have our F equals ma. We throw this force equation into that side. So that's what I have here. F equals ma. The force equation goes in there. We have an x squared. Cool. Because when we integrate, hey, we have a dx dt. We'll get to that in a second. So that's going to be equal to our mass times acceleration. Our mass, circle it is what we're analyzing. It's the Earth, and we want to know the acceleration of the Earth. So that's dv dt. So here is where you would separate variables. And I guess I went one more step because we have a mass of the Earth on both sides. So now it looks like this. We can cancel those. So now we have dv dt is equal to this. And then, well, how do you separate variables? It seems like we got 3 different variables going on here. So this is where I kind of go back to, hey, look at this. So we have, this original equation. It's a function of x. It's a function of x to the negative 2. Or divide by x squared. But this is also a function of t to the 0, of v to the 0. You know what I mean? You throw in any time, and this force is still the same. See how we have the force of gravity? And it just goes back to over here. This might make more sense. This force of gravity is only how far you are away. So if you have these two masses, and you're hella far away in ours, you're going to have a force of gravity. You know what I mean? That's holding the Earth into the sun, into its yearly orbit. Okay, so I guess this is what I'm getting at. This is a function of x divided by x squared. Cool, we see that, but it's also a function of t to the 0. It's also a function of the velocity to the 0. Because we can say, hey, the Earth doesn't have any velocity toward the sun, but if it did, even at this point, and we threw in that velocity in there, it would be a number to the 0. Any number to the 0 is just 1, and it doesn't change the equation. But it helps me understand when I'm separating variables and integrating, because like right here, yeah, we're going to separate variables, and let's do that. So we have to I don't know. I don't want to get too complex with it, but I think it's just visually, you're like, whoa, this isn't a function of time and velocity. That's also a way to say it. You know what I mean? So then when we get to here, we can separate variables. dv's on top. dt is going to go over there. We don't have any mass of the Earth, and I guess we're looking at this one. Alright, so we take the dt up here and then leave the dv there. But I'm going to put the dv on this side because we want the equation for velocity is going to be gravitational constant, mass of the sun, divided by x squared times dt. Cool, and now we're going to integrate. You know what I mean? And so here, I guess that's why I didn't like this v naught over here, because I didn't want to like divide by v naught. But anytime you're just integrating this, you're also just integrating dv v naught. You know what I mean? Because when you integrate that, I don't even think I'm saying that right. So let's not even do that. But yeah, if you integrate this, you get velocity is g mass of sun x squared, and as a function of time. Okay, hell yeah. Okay, yeah. And honestly, I haven't done this one, so I'm just like knowing the strategies, and so now we say velocity is dx dt, and now we have to separate variables. Let's write this another time, just so we have dx dt is equal to g mass of sun x squared t to the 1. Yeah, cool. We'll have to get dt over here, but we also have x squared down here, so we have to get that over there. You have to separate the variables for integration. So we have x squared dx is equal to gravitational constant, mass of the sun, t dt. Now we can integrate both sides. The constants can come out of the integration if that's how you like to do it, but obviously there's just going to be t squared divided by 2, and this is going to be x cubed. So we have x cubed, we have 1/3 x cubed. plus, damn it, I actually don't know where to do the constants. Do you do two constants of integration? I don't think so, because I think you can say when x is 0 and t is 0, well, I have no idea. You know, I mean, maybe I'm just making stuff up, but we're going to go gms divided by 2, and we're going to go t squared plus a constant. When time is equal to 0, what the hell does this say? What's our position? Oh, fascinating. Fascinating. This is tripping me out. Alright, hell yeah. So we're back. And this is cool because, like, I'm out of my scope. Like, this stuff was not taught to me. I actually picked up some physics books that actually kind of taught this method. And it was just like, oh, no duh. You know what I mean? It's super cool because it shows the integration process. And I think I need to take a step back. When we integrated this for t, you know what I mean, we had a constant. And what we said is we throw in time is equal to 0. This term goes away. And what's our initial velocity? We're going to say that's 0. Okay, but now, when we do the separate variables, I get that. And then we integrate. But now we have 1/3 x cubed. So I just don't think we... What I think we want to do is don't add this constant in yet. Isn't that right? And then get this in terms of x by itself. And then we'll have a function, x as a function of t. Because this is still x as a function of t. I think if you throw any t in here, you know what I mean, this side will equal that side. I think that's balanced. Like, structurally, you know what I mean, that's balanced. So what we're going to do is bring that 3 up there and then take the cube root of it. So we're going to get x as a function of t is equal to 3/2 gravitational constant, mass of the sun. Yeah, we got to do that t squared, but then we got to do the cubed root of all of that. Now we have to add a constant, and the constant says at time is equal to 0, what's our position? Well, we want to start at, oh, and this is the other thing. This is the driving factor that you can't mess up. We have to start our position at 150 times 10 to the 9, 150 billion meters. And the reason for that is that's the only thing that's driving this F equals ma equation. The fact that we are out that distance, that is causing an acceleration back to the center. And that's like the, oh, damn it. Is the acceleration negative? I think it is. Because, like, obviously, if we say the acceleration is positive and we're already at that point, that means that for every increase in time, yeah, even look at this. It's just so fascinating the way I set it up. If we said, and what's this? Oh, that's fabulous. So we have a function of x as a function of time. We solve that. We really want time as a function of position. You know, we want to know. So yeah, let's rearrange this. So we're going to have x cubed, and then we're going to have 2/3 divided by gms, and then the square root of that. That's going to be time. So I'm sorry I did that real fast, but we'll have time as a function of position, which is going to be the square root of 2x cubed divided by g mass of the sun. Okay, heck yeah. And now, now we know our position. Damn it. You know what I mean? I think I'm getting messed up because when our position goes to 0, we're going to have something like 70 days. You know what I mean? That has to be our time equation. So I apologize. I'm going to take a little break, and hopefully we fix that error. Alright, holy hell. So I had to take a huge break, but we learned a lot. You know, what we're going to get to is that we needed the chain rule, you know what I mean, when we did the integration process. But I made even a lot of mistakes on just my, even this, like this. We made one mistake, but we didn't catch it for the other things. So in my calculator, this is the actual value for the acceleration. And then at the halfway point, this b is the actual valuation of 0.02, And then so the average is alpha c in my calculator. And that's the acceleration that we were using. And so, so if we come back here, and then in my calculator, alpha d is going to be that distance, 1 astronomical unit, 150 billion meters. And so getting this time, because I messed up this time, it's going to be alpha d divided by 2, but then divided by, and this is half, that's going to be half the acceleration, that's just alpha c. And is that, no, this is alpha c divided by 2, so I'm even messing up again. So we're going to get in here, and this is going to be alpha c divided by 2. And so we get this is our time frame. So it's going to take this, and we need to get to see what that is, divided by 24. So it's going to take 36 days. So 37 days. So 37 days. Keep that in mind for the first half of the journey based on our average. But then our velocity, holy Toledo, is going to be that alpha t, that time frame, times alpha c. And so I'm going to store that as alpha v. So we have a velocity of 47,000. So when we came over here to do, so this should be 47. Thousand. So even right here, this time frame is wrong. But anyway, so we're just going to leave it at that because we just wanted to check on reality. And it was just fascinating that even doing this process, I made too many mistakes. And again, I made this kind of too complicated, but we wanted to get fairly accurate to have a good check on reality. Okay, so now we can just go back to F equals ma. Hey, we know the force of gravity. That's going to be gravitational constant, mass of the Earth, mass of the Sun, divided by the distance x squared. So, heck yeah. So now we are saying that, hey, this is x equals 0, and the Earth is at x is equal to 150 times 10 to the 9 meters. Okay, now we're going to say this is equal to mass of the Earth dv dt. Remember that? But then we got too many things going on. You have a function of velocity, a function of position, and a function of time. So you know what I mean? I don't know enough, but I just know it's too much. But so we use the chain rule, and we can get rid of the mass of the Earth, and we say that the chain rule is like, hey, dv dx, because that's what we do have. We do identify that we have an x term, and dv dt, we want to integrate with respect to time. Or do we? I don't know. Let's figure out what the chain rule says. This is, oh, I guess we don't, you know what I mean, because we have dx dt. That's the reason why. We really want a function of velocity as a function of position, I guess. And that makes sense. No duh. Like, it doesn't look that it makes sense, but when we do this, dv dt, that's acceleration, and when we have the x, well, we're shooting for an equation of velocity as a function of position, because that's what we want to integrate on is position. And so we use the chain rule, and you can see that you put those dv dt together, it just goes back together. So it's just fascinating that it seems like the chain rule, you could put any two variables here as long as they're going to help your equation. You know what I mean? So it's very useful. And then we can see that this dx dt, well, that's the definition of velocity. You know what I mean? So then we go dv dx, then we have velocity, and that's going to equal this. You know what I mean? So let's clean it up. We got g ms x squared is equal to, and I'm going to move the v on the other side, v dv dx. We still need to separate variables. So we still, maybe take that dx up there. Cool. So now we're going to go g ms dx x squared is equal to v dv dx. Okay, hell yeah. So now you can integrate, and that makes sense. With the x squared downstairs, I was just like, no, you can't just take it upstairs and do whatever you want with it. So hell yeah. So we have, when we integrate this, and you can get the constants the hell out of there, but this is x to the negative 2 dx. So if you integrate it, it's going to go x to the negative 2 plus 1 divided by negative 2 plus 1, plus a constant. So we're going to have x to the negative 1 divided by negative 2. So cool. So this side we're going to have negative 1/2. Oh, excuse me. Negative 1/2 times gravitational constant mass of the sun. I guess I'll just divide by x. Divide by x is equal to, now this side becomes 1/2 v squared. I think that's fairly straightforward. And now we can probably do just one constant on one side, but what we're saying is when x is 150 times 10 to the 9 meters, our velocity is 0. So we're going to throw that in there. So how do we do this? So we're gonna throw this into this side. So let's do that. So we have and then even right here, holy hell, do I need to actually say like, hey, the force of gravity is if I'm saying this is the positive x direction, my force of gravity is in the negative x direction. So this is where I don't like negative signs, but you will have to use them when you do integration. When we just do our problem, we just know that our we're going that direction, and we kind of chose it to be that way. But here, I think we need to say the force of gravity is negative. It is in the negative direction. So if we do just that, force of gravity negative, and we do a negative there, then when we integrate here, x, we just get a positive. I don't know. Let's find out. Okay, but let's throw this in here. So we got 1/2. In my calculator, I said theta is the mass of the sun. 2 times 10 to the 30. Alpha g is still gravitational constant, so we got 0.5 alpha g, alpha theta, divided by, and then in my calculator, I'll just go this. In my calculator, alpha d is 150 billion. So let's go back to that one, divided by alpha d. And cool, so we get that number. And then that's, so, holy Toledo. Yeah. So at this position, this velocity is 0. So now my constant has to equal this. I mean, that's all I was saying. So my constant, the constant of integration is gravitation, mass of the sun, divided by 2d, 2 distance. And d is 150 billion times 10 to the 9. Okay, so now we have that equation, and we got to get it in a form where we can actually have a check on reality. We got a half on both sides, holy hell. So we can get rid of that, and now we just have v squared plus gms divided by 2d. Okay, sweet. And so what do we want? We want an equation for velocity. Cool, because once we get an equation for velocity, then we can integrate again and get an equation for position. I mean, do we want velocity as a function of position? I guess. I don't know no more. So how do we get velocity? So we want velocity as a function of position is gravitational constant mass of the sun divided by x minus rotation, mass of the sun divided by 2d, and we're doing the square root of that. I swear this probably won't work. It'll just shock me if it does. So we have the square root of, we could factor out the, the GMS, but I don't even know if it works. So here we go. So we have alpha G, alpha theta, divided by, and then we're just going to go our velocity at the halfway point. So we're going to go alpha D divided by 2. That's the halfway point, minus alpha G, alpha theta, divided by 2 divided by alpha D. Okay, hell yeah. So we're square there. And is that our velocity? It's fairly close. You know what I mean? So our check, like this, because we just averaged, you know what I mean? We just assumed, and I guess we averaged poorly. Because it's the distance squared, the acceleration is going to be crap way out far. You know what I mean? Your acceleration is going to be crap way out far, and it's only going to be really good within, like, so if we're shooting from the first halfway point, it's just going to be garbage until you actually get in here. So the fact that it's in here, it's good. You know what I mean? It's a decent number. You can't just say it's an average scale, because it actually goes like this. You know what I mean? To even get to that number, it goes like that. So we are averaging high. That's why our velocity, we came out to 47,000, and then this is 36,000. Now I'm just explaining something that I have no idea if I have any errors here, but this is the only way I can learn, is like, hey, get a check on reality. What I would do is just take this into Excel right now, and I think let's do that, because I feel like there's just no way you're going to believe me that this is an actual equation that works unless I put it into Excel. And so how would I put this into Excel? I would say we have the force of gravity, which is negative G. Obviously we have F equals ma. This is the force of gravity side. There's a mass on both sides. So at the end of the day, we can just say negative G, mass of the sun, divided by x squared, is equal to my acceleration. In Excel, I have an acceleration. So I have at time, I'm going to say at time is equal to 0 seconds. I have a position of, and in my case, damn it, I guess I'm going to have to put 150,000. 150 times 10 to the 9. That's going to be my meters. And that's why this does have to be negative. And then I'm going to say, what's my, and then I'm going to do 1 second. 1 second. So now I know my acceleration is this. Is going to be at this position. I can find my acceleration. It's going to be negative. You know what I mean? So that means we're going to be going, so it's going to be negative 0.006. I want to know my dv. So we do acceleration is dv dt. And dv is just an equation with three things. So I can go dv is equal to acceleration dt. But now I'm pretty excited, because this is the stuff that you want. You know what I mean? You want to use some integration, but then you want to check on reality that, hell yeah, you didn't make any mistakes, and you kind of understand the process. So right here, acceleration times time. I'm just going to take an increment of 1 second. Sweet. So that means my acceleration is going to be negative 0.006, which just means I have a velocity going in the negative direction. And so if that's, so now I want to know my velocity. At time 0, my velocity is 0. But now my time at 1 second, my velocity is negative 0.006. Cool. And now I know velocity is change in position, change in time, or dx dt. So now I want to know, what my dx is. So this is an equation. V is dx dt. I can rearrange these three things any way I want. And so I can say dx is v dt. Cool. So, like if this is my, whoa. There is one thing, is like, hey, you need a separate column here. You need to find average velocity, because we found our velocity is 0 and now it's negative 0.06. We need to figure out the average between these. So our average velocity is going to be negative 0.006. I'm just going to do that. So this is our average velocity for that column. And now we, this is our average velocity is dx dt. Just even in Excel, our average acceleration is dv dt. That's what I did right here. This equation only works if this is an average acceleration. You know what I mean? At that time, this is going to be my acceleration. Cool. And at this time, my average acceleration is going to be halfway between those. And whoops, I'm sorry, it's 0.003. And so that means my dx, my equation right here, is this average acceleration times time. So now I go negative 0.003. Heck yes. And this is like dropping something off a cliff. In 1 second, I'm going to go 0 to 10 meters per second. I did that for 1 second. My average velocity is 5 meters per second. So then my total distance is 5 meters. This one, you would just want to do that in, like, you know what I mean? That's like a, you know what I mean? Look at that. Just a couple of swipes of the pen and you got that. All right, so hell yeah. So then this is going to be my change in position. And now I can say, heck yeah, my new position goes from 150 times 10 to the 9 meters. Now it's going to be 150 times 10 to the 9 meters minus 0.003 meters. You know what I mean? So, so doing this, so even just right now, like I see my first error. Like doing this in a 1 second interval is absolute insanity, because I would have to have a column all the way to, you know, almost a million just to get to, you know, that first time value. My alpha t is 31, like divided by 10 to the 6, is 3 million. So I would have to have 3 million columns here, and I don't want 3 million. If I have 10 to the 6 divided by, or if I have 3 million, let's do that, because this is my time frame. How about divided by 1,000? I would have 3,000 cells if my change in time was 1,000 seconds. You know what I mean? So if my change in time increases, my accuracy of my average velocity is worse, because I'm just taking the average velocity at this low point and saying that's going to be the same for the next 1,000 seconds, when we know that's not the case. But in Excel, you know, you do it at least at that next time value, it updates your acceleration based on your position, because we have that acceleration based on this equation. You know what I mean? So so I don't know. I even think 3,000 is ridiculous. So we're going to do this divided by 10,000. So we're going to do 10,000 seconds and have 320 cells. So we're going to go down 320. We're going to have a change in time of 10,000 seconds. But that does change things, because now we go to our average acceleration. If we want to find our change in velocity, that equation is going to be our average acceleration, which is negative 0.006, times 10,000 seconds. So now we have 0.006, or alpha A, times 10,000. Heck yeah. So our velocity is going to increase from 0. Our change in velocity is going to be negative 59 meters per second. You know what I mean? And you know, it's almost negative 60. You know what I mean? So this went 1, 2, 3, 4. That's all that happened. You know, negative 60, and it's moved the decimal place 4 times. Same thing will happen to here. Our change in time is not going to be 1 second. It's going to be 1, 2, 3, 4. So we're going to have a negative 30 meters for our change in position. So in the first 10,000 seconds, this Earth is going to move 30 meters towards the sun. Okay, so now that we know the basic concepts of Excel, I just refuse to do voiceovers in Excel. I don't think anybody wants to look at an Excel screen. So cool. I'm gonna do that in Excel and then bring back a printout. Catch you on the flip side. All right, hell yeah. So we're back, and for sure we did it in Excel, and it just worked out great. We set 10,000 as our time frame. And yeah, we got all the values that we wanted, 0.006, and then negative 50 for our change in speed. And heck yeah. And then you have to get V average, you know, and then once we get V average, we're going to have, because it's the average between those changes, you know, if we have 0 and then that's our new velocity, v average is that 30, negative 30. And then this dx, again, it comes from velocity is dx dt. We can rearrange this equation. Dx is equal to velocity dt. It's got to be average velocity, though. You know what I mean? That's the whole idea of integration. But booyah. And this is always the case. You can always make your time, change in time, small enough where you have like a velocity here and a velocity there, and even if it looks like this, you changed your time, so now it looks like that. Because that's kind of what happens. And then even for our acceleration literally doesn't change until you get some sort of change in, you know what I mean? You're going to have that same acceleration that causes that velocity to change constant up to a point where you get far enough away that now your acceleration is different. So cool. So once you get this change in position, you add that to every, you know what I mean? You're basically getting closer and closer. And so the take-home points are at the very end, you know what I mean? Hey, you went from positive distance to negative distance, and it happens real fast. I mean, the radius of the Earth is 6 times 10 to the 6, and even when you're a few radiuses, like way far away, you know, when you're 2.6 times 10 to the 9, that's going to be 2,600 times 10 to the 6. You know what I mean? You are 26. Sorry about this, but oh, what the hell? 2600 divided by 6. You're 433 times the radius of radiuses of the Earth. You know what I mean? At this point, and then instantly you're just crashed into it in another 10. I guess these are 10,000 seconds. You know what I mean? 10,000 divided by 360 divided by 24. These are 2-minute intervals, like every 2.7 minutes. So you go from like, the Earth is really close to the sun to the Earth is now crashing into the sun. But the big take-home points were heck yeah, were the halfway point. You know what I mean? Because we start at 150 billion, or that's 1.5 times 10 to the 11, and so we want to half that. So we want to get to 0.75 times 10 to the 11. But that's going to show up on here as 7.5 times 10 to the 10. So we go right here, and we get this is where we get to the halfway point. This is the time for halfway, and we find it's 52 days. And I totally forgot, but yeah, we're trying to figure out what our velocity at the halfway point is. So here's our velocity at the halfway point, and our equation should come out to be 42,000. But again, we're still taking a pretty decent chunk, 10,000 seconds. So this isn't going to be wholly accurate, but that's why we do it. Now we're going to go to our equation, and what did we have? I mean, let's see if we can kind of just scoot our way back. Oh, there it is. Is that it? Is that it? Yeah, that should be it. And we get 36,000. Man, so I guess I'm off here, and that seems like we're off by too much. You know what I mean? So now what? And what was our? Yeah, I'm going to take a pause and see why that is off. Alright, holy hell. You know what I mean? Oh, no, never mind. I think we're good. I thought my integration was just totally screwed. I was just like, you know what I mean? You always check for those squares. But did we do it, you know, let's I guess go over this one more time. We have x squared here, and we rearrange. We're going to have that negative. Yep. We're going to have, this is x to the negative 2. We're going to negative 2 to plus 1 divided by negative 2 plus 1. It's going to be negative, oh, holy Toledo, holy, yeah. So it's just so fascinating. I tried to slow myself down here. You know what I mean? It's just fascinating when you find mistakes. But I have no idea why you wouldn't learn all the different methods so you can find mistakes. That I think is where my videos are going to be kind of golden, because maybe you can spot them fast, but like I will try to spot all my mistakes within the video. And that's going to make you quit engineering so fast if you're just like, I can't stand making mistakes, I don't know where I'm making mistakes, and I can't find them. But yeah, it's just the little things. Holy Toledo. -2 plus 1, obviously that's -1. Why the hell would I think it's any different downstairs? So this becomes -1 downstairs. So we don't have this. So and that's this integration. So we don't have -1/2 downstairs there. And that means once we integrate, we this is negative, but we don't. Sorry, it's a little bit. But anyway, so we have negative GMS divided by x at position 150 billion. Then our velocity is 0. So cool. So our so we have to so throw in 0 for our velocity, but that means our constant is going to be negative GMS divided by d. We're saying this is our distance. So, whew, my goodness. So this is just that. And now here is our, here's our velocity. And then, you know, so crazy. I mean, this is fascinating. I mean, I'm not going to be like, oh, no duh. But this is where you want to get to be no duh. Where you're just like, oh yeah, this equation at my position initially where it's equal to d, look at that. My velocity is 0. So that's totally spelled out. So every equation usually has those no duh moments. You know, usually at the beginning where time is equal to 0. At this, it's when position is equal to d. We have 0 velocity. So now you can totally see that. And let's rearrange this, because now we have a check on reality, and I'm pretty confident that's going to work. Alright, hell yeah. So this is going to be the square root. We're going to factor out that gravitational constant mass of the sun, and now we just have x minus d. And yeah, just get a nice little sexy equation. Cool. And so we have the square root of alpha g, alpha theta, and then our x value. This is going to be alpha d divided by 2 minus alpha d. It seems like we're going to have a negative. Yeah, no duh. I have to make sure I don't forget about this negative. So this said negative GM. See, I added the negative at the end. So we have negative GMS x. That means my constant of integration is going to be positive. Oh, this is just kind of a nightmare. So if this is negative, my velocity is 0. My constant of integration, oh, it has to be negative. Okay, yeah. But this is still negative. Holy Toledo. So I just have a negative on both of these. So, cool. I could factor out a negative and get it to be back to being sexy. So we got negative GMS, and now we have x plus d. No, is that gonna? You can't do that, right? Well, and then. Oh, okay, so negatives are just, I don't like them. Okay, it goes back to this, holy crap, it goes back to this negative. So yeah, I apologize. So force of gravity is negative g ms x squared. Mass of the Earth cancel. It's equal to the chain rule. Cool, and this is velocity v dv dx. Get the dx over here and integrate this side. This is going to be x to the negative 2. So when we integrate x to the negative 2, we get x to the negative 2 plus 1. This becomes x to the negative 1. Cool, it's just an x downstairs, right? And then we divide by negative 2 plus 1. That's multiplying this by a negative 1. But guess what? We already had a negative. So this is the term that becomes friggin' positive. Holy Toledo. And then, so this is positive. When velocity is 0, oh, I'm not liking this at all. When velocity is 0, oh no, I apologize. When this position is D, when we throw that in there, our velocity has to be 0. So, you know what I mean? If this is an equation for velocity, even though it's wrapped up in this x squared and this 1/2 1/2. Oh, and does that mean this 1/2 stays over here? Yes. I need some paper just to kind of clean this up just a little bit. Actually, you know what I mean? This is also a skill where you're just like, I need a fresh sheet of paper. This is going to take me 2 seconds to get there. Okay, hell yeah. So, you know, it really is 2 seconds. Force is equal to mass times acceleration. Force of gravity is what we throw into this side. And we have G. And then we know this is the mass of the Earth. You know what I mean? So, and we know that the gravitation has mass of the Earth. So I'm just going to go G, mass of the Sun, divided by, and the force of gravity is that x squared, is equal to, and this is just d dv dx, and then times velocity. We just did the chain rule just all in one step, and that is a good skill. Go back to see the chain rule, but it's way better if you can skip all those steps sometimes. You know what I mean? It's a good skill to have. Alright, so now the dx comes up here, and we got v. We're going to integrate this. This becomes negative g ms x. Done. You know what I mean? Because this was x to the negative 2, becomes x to the negative 1. And then we have a negative 1. Alright, but this one still keeps its half v squared. Cool. Now plus a constant. Velocity is 0. No, at position where this is d. So that value has to stay. Our velocity is 0. So yeah, we're going to have this be it's gonna be negative. I think so. Our constant of integration is negative g ms divided by d. And I might be messed up on this. That's why we have Excel to figure this out. I'm not strong in integration like this. Okay, so we're gonna have negative gms divided by x, and then bring this to this side. We're gonna have plus gms divided by d, because yeah, these were negative, but this is on this side of the equation. Or it doesn't matter. You could put the c over here and then have this v. But yeah, these have to be, and this is equal to 1/2 v squared. So we just multiply by 2, and I'm going to do 2 steps at once. I'm going to go negative 2 gms, and now oh, and did I just do a horrendous error of yeah, what the hell? You know what I mean? It's so fascinating. You're like, what? That made no sense. Like how am I making those errors? Like, I'm a little bit low on blood sugar. I didn't mean for this video to go 4 hours. But yeah, that is an apologetic error. You know what I mean? There's no reason for that. Obviously, all that, whatever I was doing has to be 1 divided. That's all downstairs. So I'm glad I redid this, because now we have 1 divided by x. Oh, and am I going to factor out a negative? You know what I mean? If I did that, yes, it's 1 divided by x minus 1 divided by d. I mean, I guess if I'm factoring out a negative gms, there is no negative over here, so this becomes negative 1 divided by d. I guess I'm satisfied with that. Not really. I wish I didn't do that, so let's not do that. Let's go, I'm just going to factor out a 2 gms. And I'm going to have negative 1 divided by x plus 1 divided by d. And that's going to equal now just v squared. And then so I would square root it to equal v. And now I'm just going to clean this up. V as a function of x is equal to the square root of 2gms, and I just want to flip these. 1 divided by d plus, damn it, 1 minus x. Okay. Holy Toledo. And now I think, you know me, I got all excited way too early before. It's just like, shoot, I'm just making errors. But I do really appreciate making errors, seeing where I make errors. I don't try to make, no one tries to make errors, I swear. So there you go. So hopefully, well, let's see if this works. Square root 2 alpha g alpha theta. Now we got 1 divided by alpha d minus 1 divided by, and this x, this is going to be at the halfway point. It's alpha d divided by 2. It's half the distance. Alright. Whoa. Not a real answer. Yeah, no, it should have worked. Oh, yeah, man, these negative signs are just, they're killing me. Okay, I think I have something, you know, this constant of integration. I think I'm maybe royally messing something up. I need to take a break. Catch on the flip side. Alright, hell yeah. No. So dumb. You know what I mean? I said these negative. I got to incorporate more negative signs because you can't integrate without them. Because you can't just specify a direction, else you're just going to get nonsense. You know what I mean? You know. So it's very important when you do integration. So the gravity is negative g, mass of the Earth, mass of the Sun divided by x squared. It has to be negative over here. So damn it. You know that was the only thing I forgot. So then when we integrate, this becomes positive. And now this has to be a positive GMS divided by D. And then so when we have this one's going to be positive, but now this becomes negative. Okay, hell yeah. Whew. And now we're still multiplying by 2, but now we have 1 divided by x. We have this scenario, you know what I mean? So we get to here, and then I flipped it over. So now we're going to have, this is positive, and we got the velocity as a function of x, the square root 2gms, 1 divided by x minus 1 divided by d. You know what I mean? And it's just so fascinating how we were just off just by a little bit, just from that one negative sign carried all the way through. But it's good. I'm enjoying making errors, especially with negative signs. I mean, it's not good that I'm bad at using negative signs, but I love it from the fact of catching errors. So cool. Square root 2 alpha g. Alpha theta is mass of the Sun. 1 divided by, and this is alpha d divided by 2. This is our x value, minus 1 divided by alpha d. And it still might be horribly wrong, but no, we got it. So at the halfway point, velocity at 75 times 10 to the 9 meters, 75 billion meters. We have a velocity of 42,174 meters per second. And then we go to our Excel, and we have 42,000. And it's somewhere in between here. You know what I mean? So I could average these two, and our time value is going to be really accurate. So I'm going to just add them. That's all you got to do is just add them. 42,258.2, and then divide by 2. Cool. So what my Excel says is 42,140 meters per second. So we have a pretty decent check on reality. Now in Excel, I'm not going to do this as a proof, but you just change your time value to be even better. You know what I mean? 1,000 seconds, 100 seconds, 10 seconds, or even 1 second. And you can make these Excel sheets go pretty far. I forget how far they go. I think they go down to 1 million though. Probably not 3 million. You'd have to do that on multiple sheets. But hell yeah. So now we finally have a function for our velocity, and now we can move on to the next step, is integration again to get a function of position. I mean, isn't that going to be fun? But at least I'm just so happy because, you know, you can, I don't know. I mean, I think these videos are going to be good because, like, I want to try something where I'm not super solid on, but I don't have to scratch my head The second you scratch your head for a week, like not knowing, you might scratch your head for a lifetime. You still have to, sometimes you do, you have to take a break. But I want to show from these videos is like, hey, no. I think we have the skills. Now, if you didn't know anything about the chain rule, hell no. You're not just going to make up something to get there. So let's do this. So we have velocity. This is equal to change in position, change in time, but we don't want that. We want change in position because we have, well, now what do we want? Is that right? Do we just want change in position as a change in time? Ah, damn it. I have no idea. Yeah, I think so. Is that what we want? Do we want a position function as a function of time now? I mean, we can't have a position function as a function of position no more, so we can't do the chain rule. You know what I mean? So I'm answering my own questions, but this is just fascinating how we had to say acceleration was dv dt, but it was a function, it was change in velocity, change in position, change in time, and that was dv dx, and then v. I think it was because we were differentiating with respect to v, but now we're differentiating with respect for x and t. So just from that perspective of just like, you know, what the hell are they doing in the textbooks? Well, okay, so so we have dx dt. We have an x variable, and the only other thing is the dt. We can just set that to one side and integrate. Cool. So let's see if that works. Who knows? All right, so we're going to have, and if we do that, so we can just separate variables right now. We have to get this crap downstairs and then the dt upstairs. So we're going to have dx divided by, and I'm going to do this way, 2gms. That's a constant, but we have 1 divided by x minus 1 divided by d, holy Toledo. And so this is to the 1/2 power, and we're going dt. Hey, this side's easy when we integrate. This side just becomes t. You know what I mean? So now we have time as a function of position. But this one gets ugly. And I can't even scratch my head on this. I definitely, like, I have no idea. I mean, in essence, we have something that looks like this. We have a dx divided by 1 divided by x. I mean, I guess just, yeah, no, we have to do that. So we have 1 divided by x plus a constant. And now we're, even though the constant's negative, and then we got to the 1/2 power. And we have to integrate that. And this is, yep. Yeah, I don't know. You know what I mean? And if we integrate this value, if like we integrate this term, we have an x to the negative 1. If you integrate that dx, obviously you get, you should always write this out before you do the natural log. You get x to the negative 1 plus 1. That's cool. That's just x to the 0. I can live with that. But now we have negative 1 plus 1 downstairs, and that's 0. You can't divide by 0. But the cool thing, even if you want to just get an approximation, you can go x to the negative, I would do 0.9. Because if you go x to the negative 0.9, hey, that's pretty representative of x to the negative 1. And if you integrate this, it's going to be x to the negative 0.9 plus 1 divided by negative 0.9 plus 1. And you get x to the 0.1 divided by 0.1. So you get 1/10 x to the 1/10. So this is a representative of natural log. You know what I mean? Even just with powers of, even with the number 10, this is natural log of x. So that's pretty cool. It's an approximation that you can use. It'll probably be fairly close. It probably won't be accurate at all, but it will be a fairly decent approximation maybe. It at least tells you what's kind of going on. Alright, sweet. So I have no idea. I have to look this up into a chart. I mean, that's the only way. So I'm going to break out my books, take a little break, catch you on the flip side. Alright, hell yeah. So I think we're pretty much on the home stretch, and man, this book is invaluable. It has a table of integrals. This is Eschbach, College Edition, Handbook of Engineering Fundamentals, and it's cool. I was kind of looking up my integration, and I guess what I'm saying is we might not get to why why don't we crash into the sun? My bad. You know, it's because we have a lot of velocity that way, and we're just not, the gravitation's not going to suck us in. You know what I mean? And so, and even if we were approaching with a velocity, and then at some point we just have the same velocity that we have going around the sun, and we hit that point and we actually didn't hit the sun, well, we would just be in orbit. You know what I mean? That would be the point where the force of gravity and our tangential velocity would lock us into orbit. You know what I mean? So that's why, you know, that's why two things, it's very difficult to crash in. But this might not be the video for me to explain. We might. If I have, I probably need to, you know, at some point got to go to bed and stuff. This video is hella long. But yeah, I want to explore that. What I want to explore is if I can come up with the escape velocity equation on my own. I think it is. I think the escape velocity equation is just one that's just like, well, if you use F equals ma, it just becomes obvious that to stick into an orbit, you have to have some sort of your tangential velocity and your mass have to match, where like booyah, you just got locked into an orbit. If that doesn't happen, I think you're gonna skip. You know, so but man, I think I need to explore that more. But yeah, we are gonna finish with this integral, and just another huge mistake is just like I was trying to look for my integral. You know what I mean? It's just like, why isn't there 1 divided by x and then square root all that? Because I'm an idiot. Nah, but it's just kind of interesting. So we got to here. This is my velocity equation, dx dt. We can separate variables. dt goes there. We can take all this downstairs. But, whew, you know what I mean? Oh, damn it. I was thinking it was, I thought I could just like square, I don't know. I guess I'm going to play around with this, you know what I mean? And just for a second. So if we get the dt upstairs, this comes downstairs. I was thinking I could do this. I could go dt, and isn't this, I thought I could just, square this dt and then make this into a more logical term. But I don't think I can. I'm going to take another break. Alright, hell yeah. So we went to Wolfram Alpha and then threw in that integral, you know what I mean? And man, I am fading fast, but it was just fascinating because we threw in this and we factored out the 2 GMS. So we got 1 divided by 2 gravitational constant mass of the sun. And then there's 1 divided by x divided by 1, and then the 150 billion. But then it was just fascinating how Wolfram Alpha said it's just like, oh, you know what I mean? Because 6 times 10 to the negative 11, or 6.67 times 10 to the negative 11, I was just fascinated. That's just 6.67 divided by 10 to the 11. And I'm just like, no way. You know what I mean? Because I was just like, oh yes. And then I had to think about it for actually quite a while. 6 divided by 10, oh yeah, that's just 0.6. And I was just confused. It seemed like 6 times 10 to the negative 11 is just like 1 divided by 6 times 10 to the 11. But now I will not make that mistake because it's absolutely not. The 6 has to stay upstairs. The 10 to the 11 can go downstairs. That's what the negative does. But just solely on that. And it's just funny that you just have, you know, that's why I could just multiply these things and not put parentheses. Okay. But now we have to double check. I have no idea if this is even going to work. So this is plus a constant, you know what I mean? So this is the Wolfram Alpha just kind of does your integration. And what the hell did we say this was? Well, when we integrate both sides, we're going to have t. So this is t as a function. So we have t as a function of position, time as a function of position, and that's what we want. We have this in Excel to double check, so we can be like, well, at position 7.5 times 10 to the 10, you know, 75 times 10 to the 9, 75 billion meters. We should have that time pop up. And then at position 150 times 10 to the 9 meters, hey, that time is going to be 0. So when we throw that in, and check that out. So if you know, this is just going to be 1 and this is going to be 1. So if we throw in x is equal to that right there, these become 1. And now we have 1 minus 1, square root of 0 is 0. Square root of 0 is 0. And that will be 0 times, this is all a product, but this will be 0. 0 times, even if this is 150 billion, that'll all be 0. And, I guess this was the inverse tangent of 0. Inverse tangent of 0. I'm just getting ready for an error. No, that's still 0. Cool, so we have 0 times 0. Oh, hell yeah. So our constant for this is 0. Tangent of 0 is 0. 0 times this is 0. Now this is 150 billion, but this is going to be 1 minus 1 is 0 times a number. And then, yeah, perfect. So our constant is 0, and we have an equation. Now we just need to maybe throw it into our calculator. And let's do that. What should we do first? Should we throw it in as a graph? Yeah, I think so. So we're going to go negative 0.123423711 square root of, and in my calculator this is just alpha d, you know what I mean, divided by x. Perfect. Minus 1. Outside is going to be alpha d again. No, it is the x term. Sorry about that. Alright, so and then minus 3.55667 times 10 to the 6. And now, yeah, I don't have to put parentheses around this because this is just a product of that and a product of that. Cool. So now I can just go inverse tangent. Whoa. Inverse tangent of the square root of alpha d divided by x. Inside the square root is minus 1. Alright, heck yeah. Now we're there. When we graph this, we're going to have our x is going to be time. And we're going to have a max time right here is going to be the max time. Oh, I should have highlighted that. But we have basically 6 million. But yeah, we can go 6 times 10 to the 6 million seconds there. And then our y, what is this going to say? So this is, this is time. Oh, sorry. So this is my y value in my calculator. And as a function time, so my y value has to go from 0 to 6 times 10 to the 6. My x value will be my position. It's going to start at alpha d, 150 times 10 to the 9. But we're going to go 0 to 150 times 10 to the 9. Cool. And then we can graph it, and hopefully we get something cool. Probably won't work. Oh man, that didn't work at all. How about zoom fit? Okay, we got something going. Alright, hell yeah. So we're back and we took a huge break. And, you know what I mean? I gotta go to bed, but we are at least going to know that this integral sucks. You know what I mean? I think I already showed you I threw it into Wolfram Alpha and we got that far. I also threw it into integral calculator. You know what I mean? So bummer. I didn't do this one right at all. It should be 1 divided by. So, actually, yeah, I'm going to go back because Wolfram Alpha sucked. It didn't really work. Maybe this integral calculator will work if I actually set it up right. It's got to be my integral. See, if I bring the dt up there, you know what I mean? This has to be dx divided by, and then dt. So, yeah, let's give it 5 more minutes. Alright, hell yeah. So we're back and we put this into integral calculator and we definitely got one. It totally clipped it. Alright, hell yeah. So here is the integral and we put it into integral calculator. And the only thing that I didn't know was like, well, what are these negative signs? You know what I mean? So we got that one right, but maybe I messed up this one. I was just like, oh, you have to do everything on the inside. and then take the negative. So I'm going to insert, x minus, and this 150 billion, that's just d in my calculator, so that's pretty simple. But yeah, I'm gonna take, basically I'm gonna say, hey, okay, all that's in parentheses, and then whatever the value is, then make it negative. I've never seen these negative signs without, you know, parentheses to. Okay, so then we'll get this. Because I was getting the graph like flipped. You know what I mean? I couldn't get a positive graph out of this. So, okay, now we're going to graph it. Yeah, the graph is still negative. And, you know what I mean? But I'm just going to go with it. Yeah, everything looks good. But I'm going to go for the value of 0. And then we're going to take, you know, this is our Excel sheet. And so now we can just trace out, we're going to go for, we're just tracing out. What this graph is now we have time as a function of position. So all this is position. We throw in position and you get time. So we can actually just take a value of 75 times 10 to the 9. That's the halfway point. And that's on this page. This is halfway. And we should get a time of about, this is 4,571,000. So that's like almost 100% right on. Or that's good enough, you know what I mean? Because our distance at halfway is somewhere just right around there. Yeah, so that's a check on reality. And now we'll go to a value of, I was just happy this is like working out just a little bit better. So now a value of, what are we calling this? See, this thing's going in the opposite direction. We had to start at 0 to 150,000. So now we're going to go a value of 150 plus 75 times 10 to the 9. Or what are we talking about? No, the whole thing's 150. So we want to go 75 plus 37.5. There we go. And I don't even know if it'll actually do that. Yeah, it will. So perfect. So that's going to be 3/4 of the way, and we have a time value. Shouldn't our time be increasing? Oh, damn it. You know what I mean? So now trace this out. What does this graph even mean? It says when we are at a distance of 150 times 10 to the 9, that 150 billion meters. Our time is our time is 0. Oh yeah. So going this way. Yeah, no duh. So my value has to be 37.5, and that value of 37.5 times 10 to the 9. This is the 3/4 way. So man, the graph is just backwards of how I did it. You know what I mean? When you get to here is the sun, here is the earth. Yeah, times 0, when you're out there at 150 in the x direction, this is position. So we have a position out here. 150 times 10 to the 9 is out here. The sun is right there, and then we're just basically we're doing time in this way. It's negative. But at the 3/4 mark, let's do a check on reality. We should be at 5.2, and this is 5.2646. And so we're pretty darn close. You know what I mean? That should be right about there. 5.26. Yeah, that's about halfway. Cool. So our equation works. I'm gonna end the video with just like a rundown of calculus, of just like, well, what the hell did we even just do? Because we got this. We definitely, with the chain rule, got a velocity as a function of position. Velocity as a function of position, which was the square root of t gravitational constant, mass of the sun, 1 divided by that position minus 1 divided by that total distance. Cool, of 150 billion meters. Now, what is this? You know what I mean? So this is meters per second on this side. You know what I mean? And then a value of meters. So if we graph this, it's always good to be like, hell, well, what is this? Well, this is your y side. This is your x side. So we're going to say, hey, meters per second is on this side, and we're going to know our velocity at any position. So at position, this is where it's kind of interesting, because 0 is the sun. That's at 0. And 150 billion, 150 times 10 to the 9 billion, it is where the Earth is. And it's got a velocity of 0, you know, until it starts picking up some velocity. So, this says, what's the velocity at that position? So we have to go all the way out to 150 times 10 to the 9 meters, 150 billion meters. Our velocity is 0. But then, so this graph is going to increase as we get close, and it's gonna be this way. You know what I mean? It's gonna be something like that. Depending on how we have this drawn, because we're gonna have a velocity of 0. Oh, check this out. I'm sorry, I have it drawn the other way, and hopefully this makes more sense. It's drawn like this. So yeah, no, we were right the first time. Oh, no, I'm confusing two things. I apologize. I'm confusing two things, because what we're going to do is all right, we got to end this video, but this is going to be kind of cool, because this is a velocity and position graph. You know what I mean? So cool. It looks like that, but it's kind of useless. I mean, it's not useless that, hey, at any position we can know our velocity. That's useful. But the integration of this is useless. You know what I mean? If we integrate, we're going to get the area under the curve. And if it was a square rectangle, its dimensions would be meters per second and then meters. You know what I mean? So if it's a square, finding the area, we're going to have meters per second times meters. Well, what the hell is that? That's meters squared per second. That's a useless term. So what we want is, you know what I mean? Like, what can we do? If we have meters per second and we have meters, like, what can we find? With these two things, we know that if we know velocity and we know distance, you know what I mean, we can find maybe time. So how would we do that? If we're trying to find time, well, you take distance divided by meters per second. Holy Toledo. Well, no. We're still trying to figure out how to integrate. So this is our equation. If all we can do is multiply these two things together, how do we, you know, if we can manipulate one, so I guess I'll spell it out, we can flip that one. We can take this one to the negative one and then multiply it by the distance. The distances will cancel and we'll have time. So what we're going to do is we're going to take this velocity equation, which is the square root of 2gms, 1 divided by x minus 1 divided by d, and this is in meters per second. Now what we're going to do is just flip it. We're going to invert it. Now our equation, whatever the equation is just going to be 1 divided by that, and it's going to have units of seconds divided by meters. Is still going to be an equation with a function of position in meters. So now our equation is going to look like this. We're going to have seconds divided by meters since we flipped it, and we're going to have meters. Whatever this equation looks like, when we find the area under the curve, we're going to multiply those two values together, seconds times meters, and we're going to get a value for seconds. So and that was kind of the easiest thing. Before I figured it out, the integration was hella too hard. I just put in my calculator. Now alpha g in my calculator is gravitation, and 2 times 10 to the 30 is theta, and that's going to be the mass of the Earth. So here we go. So we have 1 divided by the square root of 2 times alpha g, alpha theta, parentheses, I'll do a couple parentheses, 1 divided by x minus 1 divided by alpha d, that's that 150 billion meters. And cool, so now we're going to graph this, and what's our parameters? It's distance, so in our x direction we're going to be 0 to 150 times 10 to the 9. And then what's our y? 1 divided by, like what 1 divided by velocity? Holy Toledo. So it isn't, I really don't know. I'm just going to go 0 to 1,000 and just see kind of where we're at. Yeah, we got to go tiny on this. 1 divided by, I don't know, 10? No, oh, weird. Zoom fit? Oh, bummer. All right, let me find that graph. Well, I guess we'll do it. All right, let me just double check. Holy, yeah, our equations, it's getting real late. We're just gonna make mistakes 100% everywhere. So 0 to there, and then 0 to, I don't know, 10 to the 6. I forget if this graph's real small or. Holy Toledo. I didn't think it was supposed to look that way. But 1 divided by 2g theta, 1 minus x, 1 divided by x, 1 divided by d. Alpha d is still that. Cool. I'm just going to go zoom fit. There we go. Whew. Alright, so we got something. Let's trace this out, because what are the values? Yeah, the values are just real tiny. Oh, so that's the deal. Okay, so these values of 1 divided by the velocity, because we knew the velocity at every given point, it's hella tiny. But guess what? The velocity at the beginning is 0. So 1 divided by 0, the thing's going to be infinity. So it's going to go up to infinity. And yeah, the velocity, this thing ain't going to be 1. It's going to be a tiny number, because at any time besides right at the very beginning, when it's going like 0 miles per hour, because even right here it's going 50 miles per hour. You're like, right off the bat it's 60. And then 1 divided by 60 is what our graph is. But this is cool, because what were we, if we have this was 1 divided by seconds. If we just integrate under that, booyah, we can actually find the time in seconds. So that does it. And so on this calculator, you have this integral function, and I need to go value 1, So we're going to go value of 0, because that's going to be our lower limit, because we have this integral function, so we can do lower limit. It ain't determined at 0, so we have to just go 1 over, click enter, and then I kind of got to scroll all the way up to 150. Or you can just do this. Upper limit is, we need it 150 times 10 to the 9, but that's infinity. That's an undetermined number, so just minus 1. You know what I mean? And then so we enter, and it's going to take a little while, but what we're going to get is the time frame, and this is an exact answer. It's as exact as this integral. And is it doing it? Oh, damn it. Tolerance is not met. Okay, so that was too much to handle. So we're going to go value 1, and then integrate, lower limit right there. Upper limit, we'll just scale all the way to it and back it off by just a little bit. It got too close to infinity, didn't like it. Yeah, because that upper limit is 1.5 times 10 to the 11, and so we'll just back it off by 1, enter, and hopefully it captures that integral, which is just the area under the curve, what gives you the time frame that it's going to take. And oh my god, if I don't have, yeah, did it do it? Perfect. And then so it's real small on here, but it said it took and I swear, is this one not working? You know what I mean? Well, it's undershooting it. So we'll try one more time, because our value for when it's going to hit is 5.58. You know what I mean? How about 5.58 million? 5.58 times 10 to the 6, and this is 4.96. You know what I mean? So we're definitely off. Just a while ago, I was able to get it pretty good. So we're gonna go try it one more time. We're gonna go value 0, and then integrate lower limit right there. And even right here, we're missing out on some juice. But no, we're fine. Yeah, we're still missing out on some juice. So we're going to go lower limit 1. Cool. And then upper limit 150 times 10 to the 9 minus 1,000. All right, let's see if that backs it off from infinity and it can actually calculate it. If not, I'll just go like 10,000. I don't know. It should work. Probably not. I need to go to bed though. Alright, did it. Sweet. So we should get a pretty good answer. Hell yeah. And now we got that 5.58. And it is 5.586. You know what I mean? So, booyah, check on reality. It's just, you just can't get too close to that infinity. Your calculator will blow up. Alright, so this was a full video. And I think you can assess for yourself. We talked about how I just can't get here tonight. You know what I mean? Why don't we crash into the sun? But I think we've done enough, you know what I mean, easy layups to kind of understand that. That, yeah, we have a velocity, cool. Who knows where the hell our velocity came from? But because we have such a huge chunk of mass, like our velocity, we can't escape the sun. You know what I mean? But our velocity is actually or the force of gravity actually isn't strong enough. Our radius is expanding ever so slowly. Now you can see that you just can't. It's very difficult to escape. You know what I mean? And that's why if something's coming in, is if it doesn't have that perfect velocity, where it's just like, oh damn, it is now a chunk of mass, and then you have that gravitational force to go on the ride of a circle. If you have that, then you're in orbit around whatever the hell you got close to. So yeah, we'll do more videos on that. Hopefully shorter, not this 5-hour nonsense. But this was a good one because I want to make videos like this. They're not going to be that popular, but it's just like, man, can you just sit down and ask questions and follow through for 4 to 5 hours? You know what I mean? I don't know. And so that was a good. I'm pretty satisfied. Pretty satisfied. And this was cool. I'll definitely use integral calculator. That was the simplest. Wolfram Alpha, it didn't seem to do what I wanted it to do. So anyway, this was really good. Hell yeah. Thanks for joining me, and that's a video.